gonna start right now. And sorry for some technical issues. Yeah, we're 5 minutes late, but don't worry, I'll be quick. I'll give a very brief opening, then I'll introduce our keynote speaker, then let it go in. Okay? Welcome to the Computer Vision in the Wild workshop. I know it's early. And it's my great honor to give an opening to welcoming you all to the workshop on this Computer Vision in the Wild. We have a very tight schedule today, and with many wonderful talks and presentations. Okay, we know that one of the fundamental research questions of AI is how to measure intelligence, right? I think it's generally agreed that now we need to measure the system's skill acquisition capability instead of evaluating a system based on some predefined tasks. We have been doing the latter for the last decades. Now with these new foundation models, we really see a lot of emerging capabilities of large-scale language models, and very soon, and I think it's happening, we also see similar emerging capability in the computer vision models as well. So, yeah, over the last 5 years, we have witnessed many AI breakthroughs towards building these AI models with human-level intelligence. And these efforts can be grouped roughly into 2 categories. The first category on the right-hand side is modeling, where we see a lot of foundation models, new foundation models, which unify different tasks, computer vision tasks, natural language tasks, using a unified approach. Take the computer vision as example. On the modeling front, we see a trend of consolidating many task-specific computer vision models into a few unified computer vision foundation models. These task-specific computer vision models, we have been working on this for many, many years, are developed by following the standard machine learning pipeline. That is, for each task, we collect task-specific data and try and evaluate task-specific models and deploy these models in real-world applications. Because each task is so specific, and training it on the model architecture for one task typically cannot be used for another. For example, for image classification, we need images with labels, while object detections needs a bounding box for each object to be labeled, and a new architecture such as region-based CNN. As a result, there are many silos developed in the CV computer vision communities. Although the state-of-the-art task-specific models often outperform humans on individual computer vision tasks, such as ImageNet classification, they are far less efficient than humans to learn to perform new tasks. And to improve the cost efficiency of AI modeling, right? Large-scale foundation models have been developed using massive computer resource and data. Typically, a foundation model is pre-trained using self-supervision at scale on broad data set, and then can be effectively adapted or fine-tuned to a wide range of downstream tasks. Examples of these foundation models include GPT, ChatGPT, GPT-4, and Turing for natural language tasks, and the Eclipse, Florence for computer vision tasks. Okay. Here I use Microsoft's Florence model as an example to illustrate how it works. Right? This model called Florence is trained on massive image test data using constructive learning. And the heart of the model are the image encoder and the language encoder that are co-trained to form the so-called semantic layer that unifies a wide range of computer vision tasks through language, and equipped with this semantic layer and adaptation models built on top of it. The Florence model has shown very promising and capabilities of adapting to new tasks in zero-shot and future learning settings. And this model has been widely used in almost all the computer vision applications at Microsoft. And then now, currently, we are trying really hard to combine this model with OpenAI models for next generation copilots at Microsoft. Among many computer vision tasks, there are two well-established tasks called image classification and object detection. Image classification is an image level prediction task when AI model classifies an image to one or more predefined classes, such as those defined in NIST and ImageNet benchmark. Object detection, on the other hand, is a region level prediction task when an AI model needs to locate and detect salient features, objects in an image. Like image classification, meaning object detection benchmarks use a predefined set of object categories. And however, in real-world applications, we often need to detect hundreds of thousands of objects that are never seen in the trained data. And we call such tasks computer vision in the wild, or CV in the wild. Our mission is to develop AI models for computer vision in the wild tasks. In the last year, we host two challenges based on last year we host two challenges for image classification and object detection, respectively. And this year, at the workshop, we're going to host two new challenges. The first one is segmentation in the wild. It's an open set instance, semantic, panoptic segmentation on dozens of segmentation data sets in real-world scenarios. The second, we call RoboFlow 100 for object detection in the wild. Actually, this is an extension or augmented version of our last year's object detection in the wild, or OD in W challenge, by increasing the data sets to hundreds of objects to cover more diverse application domains. Now we have a full-day agenda today. We have a lunch break and then resume the workshop at around 1:30. And in the afternoon, we will have 4 individual invited talks and post session and panel discussions. So really hope that you're gonna enjoy the workshop today. Okay, thank you. Now, I've been talking about a lot of things. I'm pretty sure in a week or two, you are not going to remember anything I said. But probably in 5 years, you're gonna still remember that you're gonna meet in person. Andrew Ying today. Okay, let's welcome Andrew. Yeah, I don't think I really need to introduce Andrew Ying to everyone here, but if you don't know who he is, probably this is not a workshop for you. Yeah. Thank you, Andrew.
Hey, so thanks, Calvin, Chen, with all the organizers happening here. It's good to see all of you. So, let's see. Session screen share on Zoom, right?
Yeah, and you also need to share your screen. Already there. You have this one?
But I don't have any module.
Then that's fine.
So you need to turn on my.
It's like you're adjusting the 10%. All right. Oh, awesome. Oops, sorry. All right. Apologies. It's surprising to do.
Yeah, I should leave first. I think you.
Where's the button to switch this over? Do you know this Microsoft software? How do you do that? How do you reverse that? Oh, what? Maybe it's okay. All right. Anyway, what's the Microsoft? So I'll let him fix my problem. So I'm working at Microsoft Research, not product team. Oh, I think I need to switch. Yeah. Okay, cool. Okay, thank you. Yeah, all right. All right. So great to see everyone. What I'd like to do today is share with you some things that my team at Landing AI has been working on to make computer vision easy. And along the way, I want to share with you 3 trends. That's what we're seeing, that in terms of why this is important and how to make computer vision easy, that I think will affect the work of all of us in computer vision. Oh, actually, I think I stopped screen sharing, right? And restart that. Resharing? We need to switch to swipe the display. Yeah, this one. Hit this button. Just the present. Okay, all right. So and today I'm actually going to try to attempt some live demos as well, for which I have no video backup. So we'll see. We'll see if they work. So first trend, spend more time thinking about why isn't computer vision, or for that matter, machine learning and AI more widely adopted. So if you were to take all current and potential computer vision projects and sort them in decreasing order of value, I think you get a curve that looks like this, where to the left of the curve are the incredibly valuable computer vision systems where you can build a single model or single computer vision piece of software, and that generates, I don't know, like $100 million or $1 billion kind of value worth of project. But once you go outside the tech industry, where we work on things like face rec, driver assistance, image search, and so on, once you go outside the internet sector, we see projects like these. This is a real example, disguised slightly for confidentiality, but we're working with a pizza maker that needed to take pictures of the pizza to make sure that the cheese is spread evenly. So unlike the $100 million or the $1 billion projects that big tech is good at, this is like a $5 million project. But the recipe that we figured out of hire a dozen engineers, have them work for a year on a project, this doesn't work for a $5 million project. Or this is another real example. I was working with agricultural machinery. Turns out if you can take pictures of a field of wheat and figure out how tall the wheat is, whether it's bent over because of rain, then so you can adjust the height of the harvesting arm to chop up the wheat in the right place, then you get more wheat out of the field. The wheat's already found, this gets more wheat out of the field, so it's better for the environment, more money for the farmer. And this is another like $5 million computer vision project that's kind of just sitting there. It's not economical to execute, with a recipe that large tech companies, where I had led AI teams tend to use to build these projects. Or materials grading, cloth grading, sheet metal grading, again, these valuable projects in the long tail. And the trick is, of course, whereas to the left of this curve, we have these $100 million or $1 billion scope projects. In the tail, I see a lot of $5 million projects, but there are tens of thousands of them. So the magnitude of the opportunity for us all to have a huge impact in the world is, I think, even bigger in this very long tail than in the projects in the head, which is where a lot of the attention has been. And this is not just a computer vision thing, this is actually AI machine learning thing. So one thing I shared with you a little bit is I think low-code tools are enabling the user to customize the computer vision system. I was speaking with one of the AI leaders of a large cloud company, and he said, hey, Andrew, I only have a few hundred machine learning engineers. How can I solve all these problems? And the answer is you can't, even with hundreds of machine learning engineers. The only solution is you can have tools so that the IT department of the pizza maker can customize their own machine learning system. And I think the key part of the recipe is you go to the IT department, of a pizza maker and say, hey, write a lot of code in PyTorch or TensorFlow. That's actually pretty difficult. But if we have tools to enable them to provide data instead of write code, then this democratizes access to building custom computer vision models on their own custom data. Because as I point out, the pizza maker has pictures of pizza that is what they need their model to work on. And these pictures don't exist on the internet, right? So Google and Bing don't have access to these. And so what I see today is in a realistic timeline for a commercial practical computer vision project, this is what it looks like. Get labeled data, maybe that takes like a month. Develop a model, and again, this is what I actually see, right? Having worked on this a lot with multiple teams. Develop a model, take maybe 3 months to tune it, and then find a cloud service to deploy it, set cameras up. It's like another 3 months. So the typical timeline for many valuable commercial machine learning projects is like, let's call it 6 months, maybe a year. And one problem I've been obsessed with is, can we make this easy? Can we speed this up from many months to hours, or maybe at most days? So let me share with you some stuff my team's been building, which is low-code development environment for building computer vision systems. One thing surprised me. So I like, right? I do a lot of my own prototyping in Jupyter notebooks. I actually thought when we're building this, I thought, what? This is great for someone else, but I like writing my code in TensorFlow in the Jupyter notebook. But this platform actually kind of surprised me. I realized that because computer vision is such a visual interface, I basically stopped using Jupyter, for my own prototyping. I actually use this because the visual interface just works much better for me. In contrast, when I do NLP text work, I'm very happy using a Jupyter notebook because text displays well, right? But computer vision is a very visual thing. So web UI actually makes sense. Just to show you, I'm not going to go through this, but let's see, drag and drop interface, right, to upload images. And then when this is a toy problem of detecting suits in playing cards, right? And then UI to label things, hit the button to train, take probably a few minutes. I have a few hundred images here, 300 images. If I hit train, probably take a few minutes to train a model. And then instead of a crazy complex deployment process, click over here, and then I actually now frequently deploy models like this. I'm actually going to use my cell phone to scan the QR code. Don't everyone scan the QR code and DOS outside. No, that's seriously, no, it's fine. It might work. And then let me see if I can. Oh shoot! You know what? I just realized. Let's see. Okay, cool. Does that work? Awesome. So the QR code, so we're used to taking months, right, to deploy a computer vision system, but the QR code took me to my smartphone. This is my live. Let's see. Let's take a picture. All right, there's all of you. That's me. I have a bunch of cards. And so this type of workflow that typically took months. Oh, good, it worked this time. And let's give it a hard time. I honestly don't know if this will work. My team hates it. Oh, don't know if this will work. My team hates it when I do off-script demos like this. But let's see. Let's take a photo. This may screw up. I'm actually a little bit nervous. Okay, all right, yeah, okay, not bad, not bad. Mostly got it right. Yeah, well, I think I see one mistake. Okay, anyway, all right, but again, so thank you. All right, and so with that, we can often take the workflow from 6 months down to let's say about a month, right? With this kind of easy to use UI. And then it turns out to address applications of long tail, there's one other problem we need to address, which is problem with small data sets. And Jianfeng alluded to this a bit in his presentation as well. But I gave a talk to manufacturing audience. We do a lot of work in manufacturing, and actually asked in a live audience, how many images do you typically have of each defect you want to detect, right? So we do a lot of work in detecting scratches on smartphones, discolorations in LCD monitors, dents in automotive equipment, and so on. And this is the response that the live audience in manufacturing gave me. The majority of users have fewer than 50 images per application, per defect they want to detect. So in CVPR, and in Europe and so on, a lot of us have been working on ImageNet, 1 million images, MS Coco, hundreds of thousands of images, a lot of data sets of tens of thousands of images. But algorithms tuned to these giant data sets, they don't work well on applications with sub 100 images. And for a lot of these applications, there is no more data, right? They only made 10 scratch smartphones because they don't like making 10 scratch smartphones. There's only 10 pictures in the world, and it's just very difficult to get a bigger data set. So one of the keys to getting learning algorithms to work with small data sets has been data-centric AI. This is a movement that started trying to coalesce a couple of years ago, and many people work on data-centric AI. This is observation that whereas the conventional approach to machine learning is, we know AI systems need both code as well as data. So whereas the conventional approach is to download the benchmark data set off the internet and then innovate on the code and the algorithm to then publish a paper. This recipe has worked to drive forward tremendous progress in algorithmic machine learning. But for practical applications, I find it often useful to flip the recipe on its head, which is that because of the model-centric approach, for a lot of applications, the code is just fine. There'll be an open source thing, or someone can give you an implementation of a model that works just fine. And instead, it's more useful to take a data-centric approach to development in which you even hold the code fix and just focus on entering the data. And I know that we've all known that data is important, but what data-centric AI is attempting to do is coalesce something where it becomes a systematic engineering discipline of getting the data you need to build an AI system, as opposed to relying on the skill or luck of an individual engineer, which is what, frankly, we've been doing for many years. So here's a case study. We're working with a steel sheet manufacturer. So these are pictures of giant rows of steel. If you own a car, chances are your car's body, the outside cargo, car hood, and so on, it was once part of one of these giant rows of steel. And it turns out that when these rows of steel are made, they often have defects in them. They could be carbon storing, dirt on them, or even wrinkles or dents in a sheet of steel. So we're working with a very large steel plant that wanted to find these defects using computer vision so that you don't make a car and then find that, that there's a dent pre-built into your car. So the factory internally had built a system with a 76 baseline performance of 76%, and they wanted 90% because that's the accuracy of their human inspectors. So a few AI teams, not us, went in and worked on this for months, including one very large AI company. Went in and worked on this for months, trying to tune the model, and basically had no improvement. One of my engineers went in and with our tools to help detect labeling inconsistencies, data problems, in 2-3 weeks, we got the performance up over 90%, which is the performance target. And so one thing I want to share with you with this is that the data-centric approach, it not just works, but it empowers non-AI specialists to prepare data. Because if we ask the steel plant engineers to write a lot of code, that's tough. But we ask them work with us to prepare data to tell us what exactly is a defect. Well, they're actually much more qualified than I am to understand what is good and what is bad steel. Is this an unacceptable defect, or is this just a little bit of dirt that could be wiped off? Right? They know that much better than I do. Now, just be concrete. What does data-centric AI mean? How do you actually improve the data? It turns out that this is one concrete example. It turns out that of the 39 classes of defect, one of them was a foreign particle defect, and that basically meant a speck of oil droplet or other type of dirt on the sheet of steel. And labelers were asked to label this with bounding boxes. And turns out one labeler, labeler one, was labeling it like that. So labeler one was a well-meaning, hardworking, smart, labeler, did a great job. Labeler two, given the same instructions, was labeling it like this. So both labelers, nothing that either labeler did wrong. They're both smart, hardworking, diligent people. But for months, this inconsistency was sitting in the data without anyone knowing about it. In fact, they only labeled different images, not the same image, but this is how they were labeling it. So with our tools that I don't have time to demo, we're able to very quickly find out that there was this labeling inconsistency. And again, I know that in big data, one philosophy, which I've done in some parts of my life, is say, oh, labels are inconsistent. Let's get, I don't know, 200 labels or maybe 7 labels and label a lot of data and take an average, right? You can do that for some applications. I did that myself when I was leading AI teams in some big tech companies. But when you have smaller data sets, I find it more productive to go to labelers and respectfully say, hey, buddy, do you mind labeling it like this? And this makes the data consistent and allows the algorithm to perform with a smaller data set. Because when the data is inconsistent, the learning algorithm is confused. It just doesn't know how do I output the right bounding box. It was not generating any predictions for this defect. And I think driving to that, and so for a long time, we've been relying on the skill or luck of individual vision or machine learning engineers to spot these type of defects. But data-centric AI, we're actually building tools to systematically surface these issues so they can be very targeted. To not just say, improve the data, we can say, hey guys, please look at class 23 and examine if the labeling there is inconsistent. So I want to point out one challenge that the academic research community has had with data-centric AI, which is a data-centric approach. I will frequently change the training set and I'll also frequently change the test set. If my algorithm doesn't work well in the test set, sometimes I don't like the test set. I would change the test set. But it turns out that this is incompatible with traditional academic benchmarking, where you can't have everyone test on a different test set and kind of publish papers and benchmark. So this is actually a practical problem. But this is what we should do. If the goal is, less to publish papers, publish papers, that's great. But the goal is to just get stuff to work. But fortunately, there are now data-centric competitions and benchmarks as well. My team organized one a couple of years ago, but now there are actually many groups starting to organize more data-centric AI competitions, which I think is fantastic. So with the changes I've described, we can get to faster, easier development cycle. So this, 6-7 month thing, now it feels more like a week to get labeled data and fix the data, maybe a week to develop the model, few things to tune. We do tons of auto ML style hyperparameter tuning in the background, and then a couple of weeks to deploy in production. I find that getting a camera, designing the lighting, that still is a thing if you don't already have an image acquisition system, but you can speed things up. What I saw at Land AI was we're able to help speed things up from, let's call it 6 to 12 months to maybe 1 month, right? So that was realistic. But there's one other step that I think we should go, which is to go from, let's call it 1 month to more like 1 week or even a couple of days, which is prompt-based machine learning. So this revolution has already happened in text, and multiple people in CVPR are now talking about prompting-based computer vision systems. And I'm hoping, what I see in text already is that you can prompt a model in minutes or hours, and then deploy in production in, frankly, often in hours, maybe in days. And this further makes it easier and faster and takes it down to maybe a couple of days, maybe a week to build and deploy a computer vision system. So just be clear, in this presentation, I want to focus on prompting as a developer tool. So many people, I assume all of you, maybe most of you, are already familiar with ChatGPT and Bard and Edge, Microsoft Bing Edge Chat. Many people are using that as a direct-to-consumer tool, and it's a fantastic consumer tool. But what I want to do today is focus on prompting not as a consumer tool, but as a developer tool. So making API calls to prompt interface. So just to be really concrete, this is what, if you haven't done this before, this is text, not vision, but this is what's happening in NLP, right? If I want to build a sentiment classifier, given text, classify positive, negative sentiment. In the traditional approach, I would collect hundreds of examples, label hundreds of examples, train and tune the model, find a cloud service, deploy it, set an endpoint, and then I can make predictions. This is what I do today if I'm using API calls, right? So let me just do that. And I'm going to write a prompt. So I don't know, this workshop. write a prompt. The prompt says classify text below to learn by 3 dashes as having positive and negative sentiment. That's my sentence. And then let me just make an API call and it says positive sentiment. So I just built, using OpenAI API, a sentiment classifier. And that's literally all the code it takes to build it and to deploy it. So this is happening in, I don't know, minutes, maybe hours, depending on whether you need to tune this a little bit. And so I would like to see us able to do this as well in computer vision. So given a picture like this, if you were sitting down with a novice pathologist and you want to teach them to segment out cells, right? What would you do? You kind of go to this image and point out, oh, that's a cell, that's not a cell. So what my team's been doing is, let's see, build systems to let you do that. So give an image like this. Imagine that you are a senior pathologist. You're sitting down training a junior pathologist. You say, all right, it looks like this is actually much easier with stylus. I'm using my mouse and bent over. So I'm going to say that's a cell, and I don't know, this stuff here, that's not part of any cell. That's it. That's the visual prompt. And then just as I was hitting, I don't know, Shift Enter to call the APIs, let's submit the visual prompt and then see, oops, turn on predictions, right? And then that's the predicted outputs. So I want to show you the development interface, and then, you have a model, configure how to deploy this. But afterward, I hope go play this yourself on the Landing AI website, right? So this is, I don't know, right? It's my dog. Actually, it's someone else's dog. Sorry. Right. So I'm going to train it to detect Buddy the dog, run it, and then, just like in calling OpenAI API, it took a few seconds. There, okay, not bad. And so it, right, learn the decent dog detector. And actually, let me just show you. Let's say I think the leash is part of the dog, right? So again, I'm going a little bit off script. So say I think the leash is part of the dog, so I'm not happy with this. I'm going to say, all right, I'm going to label this, as well. And then let's reprompt it. So just as you're used to having a conversation with ChatGPT, this UI lets us have a visual conversation. They go with conversational terms taking seconds, right? You can prompt it, say, oh, this is what I think is dog. I say, no, you got that wrong. I think a leash is actually part of the dog. And then, okay, cool. Yeah, sometimes it works, sometimes it doesn't. Right. And the thing is, I don't mind if it doesn't work because it just takes me seconds to continue the conversation and try to fix it. This is a real user application. So it turns out that a lot of grad students, around the world today, working to count cells on Petri dishes. So I'm going to say the purple thing is a cell. This stuff here is not a cell. You know what? Let's just give it one cell. Sometimes it works better if I prompt 2 cells, but we'll see what happens. Right. And so so this is actually many people are doing this. We actually have users using this, although this is our data, not their data. And so in kind of seconds, you can build a computer vision system for cell counting. Oh, look, and I missed one. But again, I'm not, again, if I want to redo this, I'll reprompt that. Right. So notice how I'm actually dynamically iterating on developing a machine learning system. But instead of just taking 4 hours to train, which is what a lot of my life was like, right? I've actually written letters, I've written articles about how, we wake up in the morning, do error analysis, write code, and run it for 4 hours overnight and we iterate. So instead of taking, like 4 hours, let's see, actually what I do, right? Looks like it's still running. Oh, not sure what's going on. All right, doesn't matter. Let me just one last one. So yeah, crack detection. Let's see if this works. Right. So instead of training models overnight, I actually learned something, which is if I'm training a model overnight, then every morning I've forgotten what I was doing the night before. There's a lot of mental swapping, but it turns out that machine learning development is much more efficient. If you run it, see what happens. Again, no, it's pretty good. It looks like I missed something, so I could fix it if I wanted to. So, all right. So a visual prompt is a simple visual specification of a visual task. And just point out, this is something that many people in the CVPR and broader community are working on. I actually really like the work that Meta released on SAM, the segment anything, where that would let you prompt a point or something, box an image, and it'll segment out an image. That particular approach is different than ours because you only get results on the image you prompt. It doesn't generalize to new images, at least not the code that I saw. Whereas I think for our use cases, you want to prompt one image to generalize, to recognize new dogs and new tracks and new images, not just segment out your training set image. I think Genus Painter SegGPT was actually really nice work where you can prompt it with a few, visual key points, such as parts of a people, and then have it do inference to find visual key points for new people. Barlow, kind of actually Aloysius' efforts group had a different take, and there's some different. There are actually many different approaches to visual prompting or image prompting right now. And then also just point out, there's also related work on text prompts for image tasks, right? So there's Visual Chat GPT clip, GPT-4, not yet released publicly, but demoed. And I feel like I just want to point out maybe something that's very obvious to this audience. I'm going to point out text prompts by themselves are not enough because many vision applications use highly specialized images. I can't imagine training a pathologist to recognize this using only words, or if we're detecting defects in LCDs called mover, manufacturers have very finicky, very specialized specifications for what is a defect on an LCD, and we don't have English words or other language words to describe it. The only way to train human laborers is with, frankly, visual instructions and even silent imagery. A lot of things we detect, we just don't have a good, English language or other languages ways to describe it. And if I can step back a little bit, I'm gonna on this slide and the next slide, forgive me for vastly oversimplifying, but there's a major trend in computer vision that I'm excited about. As we're walking around CVPR, yesterday and today, I feel like there's something in the air right now, and probably many of you are feeling it too. But I think the text prompting or the ChatGPT revolution is coming to vision. And here's one. I'm going to vastly oversimplify. So the Transformer paper was published in 2017 by my former team, the Google Brain team. And then since then, over the years, tons of innovation with GPT-2, I don't know, what else, GPT-3, Lambda, GitHub Copilot was the first commercial application of this that I was aware of. Then InstructGPT, GPT-3, Bard, the Bing chat, and so on and so on, right? So that already happened in text. Vision Transformer paper was published, about 3 years later. And since then, I've been seeing a similar, what feels like a very similar flourishing of ideas and explosion of research and practice. And that's been very exciting. I want to acknowledge there are differences. I mean, for text transformers, tokenization, particularly the next token, is relatively straightforward. So a lot of work was in scaling up. In computer vision transformers with this weird patchification, masking, definition of the next token is less clear. So there's stuff to work out in computer vision. I'm not saying it's a complete one-to-one analogy, but I am seeing, if you walk around CVPR, it's been incredible how much foundation vision transformer models feels like it's taking over a lot of this conference. And I think that revolution that's already happened in ChatGPT and text is not yet here for computer vision, but I think it's kind of getting here. And I'm excited so many of us here are working to use this and make tools that are easier for others. And so over the last many years, and by the way, I remember a couple of years ago, before ChatGPT, there was a buzz in the text NLP conferences. Everyone knew something was up. And I feel like now in computer vision, a lot of people feel, yep, something's up, but we're not quite sure just what yet. And I really, again, oversimplifying, RS has been driven by large transformer networks, training on large amounts of data. Training has also been increasingly with unlabeled data or self-supervision or weak labels, which makes a lot of data available. Again, this has interestingly been trickier for computer vision, defining the objective than text. But with that trend, and then also scaling up model and data size is helping generalize, given only a simple input prompt that specifies a task, hope specifies it ambiguously. And I think this too, and Jian Feng alluded to this just now, I think it's time to move past the stereotype that machine learning needs a lot of data. I know 10 years ago, I was one of the people that was saying, hey, everyone, let's scale up data, right? And model size, and that's carried us quite far. And so the last decade, I think a lot of teams did great work scaling up labeled data size, so train on 10,000 labeled images specific to your application. But what's happening now is, in this decade, I think this decade, last decade was a decade of scaling up labeled data sets. This decade will be the decade of large pre-trained models, where you do pre-train a model on a giant, massive data set. But in addition to that, you need only a small number of new examples specific to your application. And so, it is true that machine learning needs a lot of data because you use a ton of data to pre-train our models. But now, with this pre-training capability, we routinely help users build and deploy systems with dozens of images, even fewer, or maybe hundreds, but dozens happens quite frequently. I hope you try out the visual prompting thing. Just kind of full disclosure, I want to be careful about saying the limitations. Our current implementations of visual prompting is much better at distinguishing based on text and color than on shape. So this is like the worst possible example. If you take this image, upload it to a visual prompting interface and label it, you find that it does poorly, and if you iterate, it'll plateau at a very low level of performance. So recognizing cats versus dogs or shape is like the worst possible example for visual prompting for our current implementation. But this is future research that I think will make it better on. And then one other tip, if you try out visual prompting thing, which I hope we're taking a very data-centric philosophy where the system is labeled for few but accurate labels. So we assume that you don't need to label a lot of pixels, but we assume every labeled pixel is correctly labeled. And so our system is actually quite sensitive to incorrect labels. So another way to say this is, if you use it, try to color within the lines. So do quite well. This is the cell counting thing on the left, less one thing on the right. Right. And so just to share with you, I've been working on a lot of practical computer vision use cases, right, with a lot of Landing AI's users. Just to share with you kind of user feedback we've gotten. Bob Chen runs a life sciences lab, and when he uses, he said, so he's trying to recognize cells, right? And it turns out if you have a picture of a lot of cells down there, to use object detection, you have to label every single cell. Like you draw a tiny little finicky bounding boxes. That's just what we used to do. So Bob Chen said, images of this dense, it's traditionally very annoying to label, but with visual prompting, just label a few cells, it becomes trivial. Other examples, so Max Shea works on a 3D bin picking set. Development efficiency of such a complex project has been greatly increased. And then there's a computer vision tech lead that gave me permission to use his report, but not say his name. For a large pharmaceutical company, he said, using a few images to detect the crystal structures, you have the time to develop and deploy a model has been reduced from months to minutes. And I think this helps with democratizing access to these tools and making it easier. All right, just one more idea and I'll wrap up, which is, as we make the speed of iteration faster and faster, instead of 4 hours to train a model and 6 months to deploy, it's like seconds to get a model working, and then maybe days to deploy. I'm seeing really exciting changes to the workflow of machine learning. So the way I approach machine learning projects now with some of these tools is pretty different than the way I used to build machine learning systems like a couple of years ago. So I'm going to share with you just one of the changes, and there's a bunch of changes, but one is the test bottleneck. With the traditional machine learning workflow, if your training set is 1,000 images, then collecting and labeling 100 images for tests is fine. It's like, 10% extra, I'll do it. So that's why we collect training sets and development sets and test sets. It's fine. But with a prompting workflow, if you need only 10 images or 2 images to prompt your model, then who wants to collect 100 images for your test set? Now, I got to work with 2 images. Now you want me to spend time collecting and labeling 100 images just to test it? That becomes the bottleneck. So this is what the workflow of computer vision projects, not all, but some of them are increasingly feeling right? And I know I'm poking at something very sacred to our community, which is a test set, but this is what's actually happening, which is we'll visually prompt an example on 1 or 2 examples, or even for a more traditional, not prompting, but object detection, I see our users upload 10 images and label 10 images and just train on 10 images. And then we'll, iteratively improve the model, taking seconds, maybe minutes, but often seconds per iteration. So if it doesn't work, relabel it, fix it, until it works well enough. And then you're done. No test set, then let's deploy it if possible in a safe way. And safe way is important. But in manufacturing, for example, if you're detecting cracks in cement, that was one of the visual prompting examples. You might have a human inspector still there looking at the thing, but have a computer vision system just make inferences, but not actually do anything to computer vision output other than record it and monitor it and gather statistics. So safe is decisions are not used for production yet. We call this shadow mode, because the vision system is just shadowing a human that's doing the work. So there's no risk of harm, right? If you deploy in manufacturing, usually this way, in shadow mode. And then we monitor performance on production data. And one nice thing about this is it helps address concept-driven data drift, right? The best test set is production data because you collect the data set, then deploy and see drift has changed everything. So we test on production data in shadow mode. And if it fails on an example, then we optionally add those tricky examples back to our data set. And then, yeah, we'll often just look at the examples and say, oh, looks good to me, or oh no, it looks like it does badly on this type of defect or on this type of thing. And let's just improve it manually with visual inspection, manual inspection of the performance on this hand-curated data set. This process is enough, I think, to build and deploy a valuable computer vision system. So you can actually stop right here and have a working system with one caveat on safety and harm that I'll talk about later. But and then only if needed. Turns out if you have a hand-curated set of, let's say, 20 or 30 examples, it starts to get annoying to have to manually inspect the output every time you tune the model. So only if you get there, then I see people start to develop metrics to quantitatively measure performance. So instead of manually looking at 20 images, you get a number out. Maybe between 10, 20 images is when most teams make that transition. And then after that, only if it's still needed, if you need to eke out that extra 2% or 5% of performance, then click the larger randomly sample holdout depth set or test set to drive further development to eke out that lost bit of performance. So this is a very interesting, very different workflow to machine learning, and I think it's actually letting teams build things much faster. One very important caveat, if you're building an application with risk of harm. So if there's a harm of discriminating against some group, or if an incorrect output could have kinetic consequences, then don't use this recipe. For goodness sakes, do collect the test set in advance and carefully measure and order the system before deploying. So that's a very important caveat if the system has okay. But I think this is just one of the examples of the changes in workflow in computer vision that I think is very interesting. I don't know how to merge this with the way we publish papers, which tends to use a test set. It actually makes these things harder to study, but this is what I'm seeing out of you. All right, last time, just the takeaways. Computer vision is getting easier, and I think this is important to democratize these tools to help many users address this long tail of tens of thousands of valuable applications. And then data-centric AI, the discipline of systematically entering the data to build a successful computer vision system, is letting us build models with 10 to 100 images. By the way, if you have 1,000 images, that's great. Use 1,000 images. But there's just lots of applications where you don't, and it's important that we get obviously work there too. And visual prompting, which is just frankly, it's kind of working somewhat now. Still a lot of work. It feels like early phases. It feels like we're in the GPT-2 or maybe GPT-1 era of visual prompting. I don't know. But there's a lot of prototyping and developing and deploying in hours or maybe in days. It turns out getting a camera, image acquisition is becoming increasingly the bottleneck. And then I hope you try visual prompting yourself after at the Landing AI website, or sign up for an account. Sign up for a free account, then just use the tools for free, and we'd love to get your feedback. And I think my team also has a booth downstairs, so come visit the team and dig more into that with us if you're interested. So I think all of these, so I tried these things, but I think all of these three trends are things that will affect the work of all of us in computer vision. And I hope that this will be useful to you. So let me say thank you all very much. I think I'm running late, so I'm going to drop off and then I'll do some stuff.
Yeah, I'm checking whether the screen sharing is correct. Okay.
It's working.
Yes, yeah, please start. Just please.
Hello, everyone. Thank you for having me. I'm very excited to be here. And today we'll talk about from object scenes, understanding the visual world with vision and language models. We here all share our interest in understanding the visual world and being able to find, detect, recognize objects in the wild. This clearly has a lot of applications, for example, in self-driving, robotics, and so on. But as you know, in order to work or accomplish those applications, you really need to have labeled data that goes beyond what we have seen. So we have to be able to detect new objects, unseen objects in the environment. Labeling costly, and of course, we'd like to be able to name things by maybe complex names instead of a lamp, the red lamp standing there. Some names can have multiple meanings. And wouldn't it be nice if we also have multilinguality? First, I'll talk how we can take advantage of large vision and language models here at ML to use to improve detection. And I'll first briefly introduce our previous work, FVLM, that was presented at ICLR recently. This is open vocabulary detection for vision and language models. How can we take advantage of these large language models to very briefly adapt our models for open vocabulary detection, detecting novel objects? You can do distillation from a very large model to a small model that does detection. You can use large models to label. And here, instead, we directly leverage the large models. More specifically, we use the CLIP model of Rapper et al. And we have a very light adaptation for bounding boxes and categories. And so here is a schematic of how that will work. As I mentioned, we are going to use the model directly and we will freeze the whole model. The model is trained from a vast amount of data over web, which is, however, noisy data. So on top of the frozen backbone for an image encoder and a text encoder, we're going to only learn a detector head that produces detection regions, scores, and so on. And so the two are correlated usually with cosine distance, and then you can, for each given text or each given input name, you can determine how well it matches a specific region, and that way you can do detection. So now, if you want to extend this to open vocabulary detection to objects you haven't seen, during inference, you would have a set of objects and names that you do not know about. These are novel to you. Here, they're at the very bottom, shown in green. Of course, because we have pre-trained language model, it will understand these concepts and will be able to map them in the encoding space. And very similarly, we can produce scores for those new categories as well. And they can tell us for a region, a visual region, whether it is a cat or a purple cat or whatever. So there's also some details because we have already trained some detector models, so you would be able to obtain scores from there as well. We use geometric mean. The bottom line is with this very lightweight approach, you're able to obtain the best state-of-the-art open vocabulary object detection algorithm. And here are some examples how it works. So for example, here it can find objects like heron, bircher, Tabasco sauce, seaplane, and so on, even mallard duck, like some very long tail categories. What is also very nice is that it is able to do to do that with very much smaller cost, about 200 times less expensive than a destination model, still outperforming it, and even our larger model is 14 times less expensive. So now we have taken a model that's already pre-trained on web images. It has nothing to do with detection, but we have found that it has a very good semantic understanding performance. What if we make our models to be detection aware where we pre-train them? We introduced the region-aware open vocabulary detector, ROVIT for short, where we'll contrastively train with localization awareness. And this model is based also on VIT, and that allows us also to take advantage of a large number of models for pre-training and so on. And we also introduce crop position embedding to make this more robust to detection tasks. And so here is very briefly what the novelty and kind of interesting things here are. First, while doing contrastive training, we use focal loss to be able to take care of difficult examples that you would have while having many detection proposals. And further, we are using crop position embedding, imagining during training, we're going to crop from a very large canvas, which is actually your inference scenario. And then from that, we'll take various crops during training, introduce them in the contrastive learning, and that will make it more robust for when you are going to apply this for detection. This algorithm works very well as well. It performs the counterparts using VIT. For example, our very small VIT-based model performs the VIT huge and VIT-L of our VIT, and our bigger model performs even better. Another very interesting side effect of that is that this approach has very strong retrieval performance. Basically, it has improved the representation learning capabilities. So just testing this out of the box, for a retrieval image text and text image retrievals, we see that it outperforms as a sort of on par and outperforms much bigger models like 1 billion parameter models. And while we have focused on object detection for novel objects, I would like to briefly mention our FindIt work, which was presented last year at ECCV, that generalizes detection in the sense that you would like to be able to detect objects, no matter if you describe them very specifically with almost like a sentence, which here we call inferred expression and comprehension, or detect more than one object, able to do all of these tasks in one joint model. And so here an example of all these tasks that our model can do. It's a multitask model. This means that it can do all of these tasks together, and it's trained for that. So for example, bottom left blue container. In this image, you have two blue containers, but it should be able to find only one of what you're searching for, or you can find multiple objects like the broccoli, or do the class detection task. And so that basically extends these models to be able to more naturally refer to the different objects that you're looking for. Although this is a small model, we found that when you combine these tasks together in multitask model, you're able to perform better and also have very good generalization to novel categories and super categories. Here's some performance results where you see that just adding this task is really helpful without extending the data at all. Okay, so here are some results from novel categories and super categories. And now I'd like to flip a coin and talk about the large vision and language models. So far, we have thought, how can we take advantage of these models and maybe adapt them and have them do detection for us, open vocabulary detection, take advantage of their capabilities. But now, how can we build those large models to begin with so that they have detection capabilities? And so some of the foundational vision and language models have definitely made amazing progress. The Florence model, for example, that Jianfeng mentioned earlier, is also able to do detection, but can needs adaptation to specific adaptations to that. And some of the other models like Flamingo, etc., aren't capable of that task. So let me introduce one of our recent works called PALI. It's a language image model with a very simple image plus text as input and text as output interface. And it can do image captioning types tasks, VQA, classification, and things of that sort, as is given in the example here. And it is also a multilingual model. PALI really show that scaling of the models, especially on the vision side, really matters. So if you compare, for example, the Flamingo model, its vision is only 0.5% of all the parameters. Whereas in PALI, we have increased the backbone for the vision side to about 20%, to about 12 billion parameter model out of a 17 billion parameter model. And we see, as you see in this graph that shows scaling from a 3B to 15B to 17B, that just in adding a few more parameters on the vision side really helps all the other tasks that are vision and language tasks effectively. And further, scaling really matters for a multilingual capabilities. I'm sorry, I lost the presentation. Oh, sorry. I would need help because I've lost the presentation.
It's because there's a the slide didn't change, so I asked them help. I entered the stop sign. Stop sharing. So that I know. Sure, the sizing stuff.
We're here. Yes. Okay, thank you.
Sorry about that.
No problem. Let's look at some of the PALI capabilities. It can do descriptions of the image. So here, for example, a clock on a building that says Albania on it, or two helicopters flying in the sky. One has a yellow stripe on the tail. So you can see that, although it's demonstrating a captioning task, you can see that it has quite a lot of understanding of what's going on in the image. Some examples in multiple languages are down below. Some more examples showing OCR, or my favorite one, what did this organism evolve from? And the answer is from the model is dinosaur. So it knows that I must be talking about the bird. It must have to localize it and then answer. Or how fast could this travel? This is for the airplane. It gives me 800 miles per hour. Or what isn't edible in this image? It answers stuffed animal. So it has quite a lot of understanding and even kind of localization capability. How about detection? Does it do detection? So in this current model, we did not demonstrate detection, but we trained the model adding a number of different data sources, and some of it was object aware. Basically, being able to know that there are several objects in the image and that they are there, or some objects aren't there. So we call this object-aware pre-training. And if you see here from the ablations, when you add, for example, OCR data or others, some tasks might be helped, some tasks might be hurt, and the object-related mix that we added, object-related data set that we added to the mix, helps all the tasks across the board. And again, these are image language tasks. So now I'd like to talk about our most recent model. It's called PALI-X. It's a bigger model, and it outperforms even SOTA that was outperformed by PALI and by larger margins, and on even more tasks. For example, infographics, additional video QA, document understanding, and so on. And also, importantly, this model allows you to do a few shots in which you are adding image and language as on the input. It outperforms all our models on the Pareto frontier on higher accuracy on fine tuning and also highest accuracy on a few short capabilities. That is to be able to allow the model to be fine-tuned, to be prompted and do task routine. How about detection? PolyX can also do detection, and it is doing so by using the simple API and fine-tuning. We use the pix to stick approach in which the boxes are represented as text. So as you can see from the examples here, it is able to detect, for example, left half of the watermelon, the right half of the watermelon, and so on. It is able to detect this is paradise text. So it has the abilities to understand things, to be able to be prompted with multiple, with the longer sequences of text and so on. While it performs pretty decently for a model that's not specifically trained for any detection, it's not quite a sorter in that domain, but it has another interesting capabilities. For example, if you say detect balls, it can give this whole union of balls, but if you say detect ball, it will give you the individual one. So there is a lot of kind of interesting understanding between language and interaction between language and image happening. And further, it can detect things when you ask for them in different languages, which is pretty incredible. Of course, we don't have benchmarks for that, but I find this a very, very good capability. And so I'd like to now focus more on large models that we make them to be detection aware. So all our previous models are generally trained, and we hope to have these emerging capabilities, which is great. But what if we demand from our models to have all these capabilities from the get-go and have this better understanding of the world? And I'd like to introduce Mammoth, which is some of our most recent work. It is a multimodal model, vision language model, that can do many more tasks than even previous models. For example, it is capable of doing image text and text image retrieval, open vocabulary detection, video question answering, video captioning, VQA. It is a much smaller model. And to put this in perspective, here are some of the previous models. For example, Florence is able to do detection, retrieval, Cocker is able to do retrieval, VQA captioning, Polly is captioning, and so on. Flamingo takes in some of the video tasks. However, our model is able to span all of these diverse tasks. And actually, it is very challenging to put together a model, especially here is a small model, and to be able to instill and be able to have all these capabilities. And so here is how we approach that. Our model is actually very simple. It's only made of a single image encoder and a single language decoder, which are going to communicate during training, of course, and inference. And our biggest challenge is to put together a captioning-like task where image and text need to be inputs and also text needs to be output. And also contrastive tasks in order to be very good at retrieval, where an image is an input, text is an output, and vice versa, and also be able to have a localization awareness while training. And so to do that, our model, as having like a single encoder, image encoder, and text decoder, basically is done by training in 2 steps. They're interchangeable, their order doesn't matter. But in the first step, let's say we have we're kind of training a contrastive to a contrastive objective where we have the image encoder produce embedding, and then the text decoder works in a bidirectional masking to also produce encoding for text, and that's applied a contrastive loss. And then in the second pass, we are now doing a cross attention where the image is also an input to the text. We have causal masking, and we use cross attention in order to achieve that. And while we do the contrastive training, our losses are such that you can have focal loss and be able to handle many more objects. We have also a CP. We also have a proposition embedding. And I want to briefly mention that with this simple model, we're able to very quickly adapt the model, adding a tube fit, which is a very simple adaptation, taking video tubes from the video and reusing the exact same encoder. And with that approach, our very small model is able to perform much larger Flamingo, PolyX, etc. On these video QA and video captioning tasks. Here are some examples of various tasks. And finally, as a conclusion, this model shows a little bit of a trend for descaling or not scaling so much. So of course, the data set that we put in the models, in these large models matters, and it has to be high quality and of diverse sources. The scale of the model matters because it has to capture so many tasks, but also how you train and how you put together all these tasks also matters, as we show with this much smaller model that can do perform very well. And here are its performances. It's above SOTA on retrieval tasks, on video question answering and video captioning tasks. It's at SOTA for open vocabulary detection, and it's slightly trailing the very big PolyX, etc. on VQA. And that work would not have been possible without all my collaborators. Thank you very much. And thank you for your attention, and I'm happy to take questions.
So hi audience, if you have any questions, please come to the mic. So if there's no question, I'll ask a question first. So I'm really surprised that you are able to descale the vision language model. Could you explain a bit more how are you able to reduce the scale but still make the model perform so well?
That's a good question. Thanks. So because we have trained with contrastive objectives and split captioning objectives, that makes the model use its parameters in a more efficient way. And that allows us to still achieve very high performance without needing so many parameters. And so basically we think that putting these two together really helped us perform very well. Of course, I'm looking forward to scaling this model because I'm very certain it will perform even better from what we have. Thank you.
There is one more question here.
Hello, so I have another question. I think PolyX models, this kind of model are super good. I remember Pani, I think it's a sort of performance on Web 1, which are very challenging task. But I think the tricky thing right now is that PolyX, this kind of models are not open source. So I do not know what's your standpoint on kind of open source, or at least to what extent we should share this kind of models to the general community.
That's a great question. For a lot of our work, we try to open source where possible. With some of these models, it's basically a very complicated way to open source the models. And for some, it is possible, for some it's not. But basically, a lot of our research, we try to open source as much as we can, both code, data. For these models, it's basically not depending on me too. Yeah.
Okay, thanks.
So do you have any more questions? Go ahead.
I really appreciate your talk with interesting research about it. Well, I have a question regarding like data sets or training in Poly or all kind of like big models. Like there was like an interesting example that given a book with the price tag, like $2 or something, but so that if that image is given to the model predicts the price of the book, right? Is this like the pair of the image and the like price of the book is included in the training set, or the model just performs like OCR like task just to simply train the model? How about like data set is figures?
So the data set is verified that no evaluation or test set is part of the training. To be able to do OCR, we added an OCR kind of data to the mixture, which is automatically generated. So basically, you artificially generate numbers and text in various scales and orientations and so on. And then that part of the data, as I showed in one of the equation, it really helps boost the OCR task. Other than that, the data is consistent very similarly to the clip data that's just harvested from the web, very noisy pairs of image and language, where they are very lightly filtered for kind of for quality and things like that, but mostly like the noisy labeled data. So you might have a lot of examples there in which you have a book of Harry Potter and then the text says Harry Potter, and the model is able to map these two. So these two sources actually help the model best for OCR.
Well, I just one more just follow up on that, like. I feel like research the poly is that like vision into like understanding for the vision or image domains, like scaling is much more important factor for just enrich more visibility power, right? But into like language domains, like there seems like scaling law seems to be like just the convergence in some way. Or for example, since referring the paper like Chinchilla, like no more parameters are the golden solution for the like reasoning, right? But is there any like intuition of you? Do you have any intuition that why do image understanding requires more scaling?
I think this is because this model is basically on the upward curve of scaling. So basically we are finding what really works and how many parameters we need. We might need a little bit more scaling there, but we will probably saturate. As I showed with the smaller mammoth model, it's 2 billion model versus 55 billion model, and it still is able to outperform on many of the tasks. So I do believe that we would not scale infinitely, and we should take advantage of using the parameters in a more efficient way rather than just adding more and more parameters. But yeah, to that question, I'm pretty sure that more scaling will help, but there will be a saturation in vision as well.
Thank you.
Thank you very much.
Thanks Amelia again for her great talk. And next we will have our spotlight session, and our first speaker is for Viper GPT. Let's welcome the speaker.
Hi, can everyone hear me? It sounds like yes. So thanks to those of you that are staying. If you have been wondering, oh, but I can't scale my model to be really big or scale my data set to be really big. All of this sounds really cool, but I can't do those things. Now, hopefully we'll be going in an orthogonal direction that will help all of us be able to add to these capabilities too. So on that note, I'll be presenting Viper GPT, which is visual inference via program execution for reasoning. What does that mean? So this is, oh, by the way, before I get into that, this is joint work with Jidak Suris, who is my collaborator over there taking picture, and Carl Vondrick, our advisor. So yeah, so what does this mean? So if you look at this image, then all of these amazing, really big vision language models that we've talked about and that we've seen in other works are really good at telling you a wide range of things about images. So you can ask things like, what are the boys eating? Muffins. Where are the muffins? On the table. How many muffins are there? 2. How many kids are there? Too many. Actually, a couple of those don't seem right. So let's think about what makes those questions different from the other ones. So a lot of these models, and this will continue to get better and better with scaling, of course, but at the current time, it seems like for end-to-end models, it's really easy to ask things like, what is this? Where is this? Like very system one type questions, if you think of the system one, system two dichotomy of like perception and reasoning kind of. But for things like how many are there, which require multiple steps of reasoning, end-to-end models kind of struggle with this kind of question. And so these results are from BLIP2, which is another one of these kind of end-to-end large, like generates text from images kind of models. So why not just scale this approach up? Let me scroll. Yeah. So why not just take image query, stick it in a big black box and get an answer out? So there are some limitations of end-to-end that hopefully I can convince you of. First is things like math and logic. This has been a big sticking point for us for a long time with neural networks is if you want to do something like division, does it really make sense to train on millions of pairs of 4 divided by 2 is 2, 100 divided by 5 is 20? We have calculators, those work pretty well. Explainability, we don't really know what intermediate results are without decomposing things further. Compositionality, if I have one big model that's, or even not big model, I have one model that does object detection really well. I have one model that does recognition well. I have a depth model. I have all of these different models. Right now, we have some techniques for kind of stitching these together and then training further to try and smooth things out and hope that they kind of all get along and are happy together. But really, we don't have good ways of composing existing capabilities. And then, of course, also hallucination of it'll just say things like, oh, of course, there are 2 muffins here. How could there be any more muffins? So our alternative paradigm for this is synthesize, then execute. So this is the program generation. We'll be executing programs for reasoning. Specifically, what we'll be doing is you take your query. So which pet is in the top left? You give an API that you've written all of these functions for a wide range of models you have. So I have an object detection model. I have a depth estimation model. I'll write an API for that whole system. So I'll have a function like find that is object detection, etc. So I'll give that API along with the query to a code generation large language model. In this case, we use GPT-3 Codex. That will then generate a simple Python function that uses the API you've given it with all of these other pre-trained vision models that will have this program of like, okay, for which pet is in the top left, I need to find the pets, sort them from top left, etc. Once you have this program that the large language model has written, you execute this using the Python interpreter and the API you've given it, giving you all the strengths of the pre-trained vision language models that you have, along with the strengths of just the Python language and like everything you get like that, like division, etc., to produce your final result. So let's see if this will work. Did not work, so let's see if we can go to the link. So yeah, so if you look at this video we have here, this kind of illustrates the whole pipeline. You generate this function. The question is, how many muffins can each kid have for it to be fair? There's some steps that you just need to do to answer this question. You'll need to find the muffins and count them. You'll need to find the kids and count them. And probably fair in this context means even division. So you'll need to be able to divide the number of muffins by the number of kids. And all of this can be cleanly decomposed into this program that you see here, where first you're finding muffins, you use the simple Python length function to count them. And this would be really difficult for an end-to-end model. Just think there's so many steps involved there and so many steps that are very difficult for end-to-end, like counting, division, etc. So let's see if I can go back to the slide here. Yeah. So that gives you an overview of what this is, and you can put in whatever models you have. You have your favorite tasks that you know you want to be using. You have some other models. The world is your oyster. Just write it in the API. The code generation model will figure things out. Zero shot. You don't need to train at all. If you're like, oh, I don't have a ton of TPUs sitting around, this can still work. So that's basically the framework, and I'll take any questions. Thank you.
So for time constraint, we will have all the questions after all the presenters. So our second presenter.
Maybe I'm too tall for this. So, hello everyone, my name is Shivan, and today I'm going to be talking about our paper, Robust Likelihood Novelty Detection. So in an unsupervised novelty detection, you have some prior knowledge of an inlier distribution P of X in terms of training data set. And during inference, when you get a sample X, the goal here is to determine whether it's an inlier or not. And this problem is also known as anomaly or outlier detection, and it is relevant enough to develop a computer vision-based system for real world. Now, in this work, we are more concerned about what happens to the input if the input is perturbed or attacked. This is because neural networks are susceptible to minor changes which could result in misdetection or misclassification. This is short summary on approaches, but there is extensive literature on this. But the takeaway here is that for supervised learning, they have designed a many defense mechanism to address this. But for unsupervised deep learning based method, there are not many. So this calls for designing new approaches in this field. Well, novelty detection can be approached as calculating the likelihood of the input P of X, and then determine whether it's an inlier or not, if the estimated likelihood is greater than the threshold gamma. Well, therefore, the main technical challenge here that we're trying to solve is that what happens when, how to make the likelihood estimation more robust to this perturbation. Well, let's assume that there is a set of perturbation, which is allowed perturbation S. And then for the inliers, the likelihood for any perturbed input X plus delta should remain greater than gamma. Similar for outliers, any likelihood of any perturbed input X plus delta should remain less than gamma. And I'm skipping a few steps here, and we take a robust optimization approach. And we impose this requirement by solving this robust prior. Well, note here that this method is completely different from the supervised learning method of adversarial training, because they robustify on a loss function, and here we robustify on a test statistic. GPND is a novelty detector method which relies on autoencoder of special properties. The decoder F in this autoencoder is an isometry and provides a parametrized manifold for input data. And encoder G is the complete pseudo-inverse of the decoder F. Well, this encoder can do two things. First, it can compute the likelihood P of X that we need, and it can also compute orthogonal projection from the ambient space onto the manifold. By using this, we can easily compute the proposed robust prior. For example, let's assume that there is an inlier distribution that represents the digit 8. Well, when we take a point X and project it onto the manifold, the point becomes f of z, which is a clear image of digit 8. Now, because of the geometry of this autoencoder, we can produce images that drifts away from this manifold in the orthogonal direction. Using this, we can produce inliers and outliers and use them to optimize the robust prior, and thus learning the robust autoencoder for novelty detection. Our result on F fashion MNIST provides a performance boost on the standard protocols. And here in the orange, the model exhibit robust behavior against the baseline blue, which is trained without using this robust prior. More questions are welcome at our poster. Thank you. Any questions?
So, is our third speaker here, Alex?我问一下他们能不能看到。So Alex will present their vision language model, and Alex is from Apple.
Thank you. Hello, everyone. This is a work done primarily by Kanchana. I'm presenting on his behalf, done collaboratively with our colleagues at Apple ML Research. And the topic is perceptual grouping in large-scale vision language models. In the last few years, we've seen pretty impressive results with such simple models, thanks to the availability of large-scale data, which has enabled image-text contrastive learning to give you really strong representations for classification and retrieval problems. An interesting question, which we have been looking at together with the community, is whether these representations are also strong with respect to segmentation tasks, perceptual grouping tasks. And the answer is in the affirmative. In particular, in this work, we present a modification of the clip work, which we dubbed Clippy, which is a small number of important, impactful changes of the clip architecture, which enable zero-sort segmentation in various setups, as shown on the right side. And in addition to this, this variation of clip called Clippy is also giving more robust representations to counterfactual manipulations. As a very short refresher, classical contrastive learning is based on visual and textual encoder, these days transformers, which embed or produce representations for two modalities, and using the contrastive laws, this representation is learned on paired modalities. A piece here is that as you use transformers, you have representations for tokens within each of these modalities, which are being aggregated in a global representations in the last layer of the network. In this work, we look at all the architectural design choices in this setup. In particular, we identify 3 points which, if modified, enable emergence of perceptual grouping in these models. In particular, it is really important to use a strong pre-trained models on both the visual and textual encoder, even if you train the systems on hundreds of millions of images, using, for example, a language model-based encoder, which is trained on substantially more textual data, is crucial. Similarly for the vision model. And further, on the aggregation point where we compute the global representation, using maximum pooling versus all the other options is also crucial to enable the system to have emergence of segmentation on the visual side. And here, for example, extensive results on top-down perceptual grouping or semantic segmentation using this approach. So what happens is that after we learn a global representation for the image and the text, we can look at underlying patch embeddings and compute similarities between the patch embedding in the image and embeddings of all possible labels on the segmentation side to assign a label to that patch embedding. In this way, we can do semantic segmentation. And we can see that on COCO and VOC, this approach outperforms the original clip as well as other approaches which look at the same problem by a non-trivial margin in a zero-shot fashion without seeing any training data on COCO or VOC. And we can see the same performance for bottom-up perceptual grouping or unsupervised segmentation, where we cluster these patch embeddings to obtain a number of bottom-up clusters in the image, and similarly using the same type of evaluation on VOC, the approach is not really better than most of the other techniques using the same setup of unsupervised segmentation. Finally, this representation happens on a global level, happens to be more robust to counterfactual interventions. In particular, there is this Waterberg data set where people look at modifying the background of an object and producing a background which is unnatural. And we demonstrate that our approach actually does get affected very little by these counterfactual manipulations versus the original clip implementation and design. In conclusion, we demonstrated the minimal set of the original clip approach can yield a representation which is really strong when it comes to semantic and unsupervised segmentation, as well as these more robust manipulations. Thank you.
So we'll leave the questions to the end of the spotlight session. And let's thank us again for the talk. Our third speaker is Nicole. Our fourth speaker is Nicole, and he will present his ESS work. On那个 screen， 没有上 screen， 这个先手把鼠标，鼠标的。你先那个，我问他一下，现在我可不可以？In present mode. I think presenter mode. Presenter mode 算了，这个没事。切下 screen。OK， 这个可以，没有问题，不管了，就这个。Okay. Sorry, we're just debugging the Zoom for the online audience, and let's welcome Nicole.
Thank you very much. Let me go to start. Okay, welcome everybody to the presentation of our work, ESS, Learning Event-Based Semantic Segmentation from Still Images. This work was done together with Xiaoning Sung, Daniel Gehrig, and David Scaramuzza. In this work, we show how we can do semantic segmentation using an event camera. Especially, this network is trained without having ever seen a label in the event domain and only use labels in the standard image domain. In general, semantic segmentation is important for many applications such as autonomous driving. Event cameras now have the potential to increase the reliability of those systems because events recorded with an event camera have a certain robustness to lighting conditions and also feature a low latency. So let me start by briefly introduce what is actually an event camera. So here on the right, you can see a comparison between a standard camera and an event camera. A standard camera outputs at a fixed frame rate dense intensity images of the scene. In comparison, an event camera only outputs a signal called event if there's a brightness change measured at the pixel. This leads to this continuous light point cloud in space and time. As a consequence, if there are no brightness changes in the scene, the event camera will also not output any signal. Because event cameras are still relatively a novel sensor, there are not many existing data sets which contain labels. So there's the big question in the event-based community, how can we actually train deep neural networks on events provided by an event camera? In this work, we now propose to do domain transfer in an unsupervised domain adaptation setting. So we want to leverage the information provided by labeled images and transfer this to unlabeled events. Existing works which tried to tackle the same question, tried different things. Compared to the related work, we have now like several benefits. First of all, we don't need labels in the source domain, which is in our case the event camera domain. We also don't need paired data, so we don't need like images and events recorded at the same time. We also don't need to hallucinate motion to generate fake events from a single image. And further on, we can also transfer from single images to recurrent event sequences. This has the huge benefit that we can leverage all of the existing image data sets for events. The key concept here is that we try to align an embedding space between an encoder for single images and the embedding space of a recurrent encoder, which gives which sees only events. By doing this alignment, we can then train a task network using image labels in the image domain. And then during test time, we can then directly take the event encoder and use the trained task network to do the predictions. To do this alignment, to do it like we have two steps. First one is in the image domain, which is the classical setting, where we use the image labels to train the encoder and the task branch. And the second step is then in the event domain, where we leverage a translation network, which goes from events to grayscale images. And here's also basically the key idea. We want to now align this embedding space of the translation vector with the image encoder, which was trained in the image domain. By doing this alignment, we can then use a task branch to predict semantic segmentation also in the event domain. To enforce this alignment, we then enforce multiple consistency losses on the prediction level, on the activation level, as well as the feature space. Okay, we then also test our method in the UDA setting, which means we have labeled images, as mentioned before, as well as unlabeled events. And furthermore, we can also test our method in the supervised setting. And this is quite an easy extension to this framework, which I showed you before, because we just need to introduce loss in the prediction of in the event domain. We show that our method outperforms existing state-of-the-art by 6.3 mean IOU in the UDA setting, so without ever seeing labels in the event domain. And this then even increases when we use additionally to this UDA setting also labels in the event domain. In this case, we also achieve state-of-the-art in event-based semantic segmentation. So in general, or in conclusion, our method can be applied in new driving scenes without requiring semantic labels for events. It is also general purpose, which unlocks existing labeled data sets for other tasks in the event domain. And yeah, this also paves the new and exciting research directions in new and previously inaccessible fields for the event-based community. And this is my talk. Thank you very much.
Thank you, Nico. And our last spotlight presenter will join us virtually.
不是在这里面吗？
不是，它是放在这儿，
我没收到哪里的。
就是 drop link， 就是那个 spotlight。
没有。
你把浏览器打开，或者是加开。
哦，这个是吧？
对。那直接在这儿放吧，我觉得。我们还是找点。
来不及，感觉要不让 Jacob 先讲算了，这个。哦，可以。
直接能放。
可以，就放这个，就这么放就行。
share screen。
share， 你问一下他，重新 share 一下。
等一下，是，然后 sorry。
我觉得我们就让 Jacob 先讲，其实最好。
I introduced about GCD. Let me first introduce a bit about NCD. Hello, everyone. Today, I'm going to present the paper Imba GCD, Imbalanced Generalized Category Discovery. This paper is conducted by Ziwin Li, Ben Dai, Furkan, Christoph Meiner, and Haojin Yang. So even though this is a 5 minutes talk, we also have a table of contents. So before I introduce about GCD, let me first introduce a bit about NCD. So in NCD setting, we have a labeled set and unlabeled set. And the classes in the labeled set, we name as known class, while the classes in the unlabeled set is unknown and is different from the labeled set. The goal of the NCD is to discover the new unknown classes in the unlabeled set by leveraging the knowledge from the labeled set. For GCD, it's more realistic setting. This time, in the unlabeled set, we not only encounter unknown classes, but also the known classes. For example, cat, dog, and rabbit, which are in the same classes in the labeled set. It seems incremental, but the problem becomes more challenging because we need to classify unknown classes from known classes. And unknown classes are easily misclassified as known classes, which makes the problem more difficult. In realistic GCD, we think that there are two main challenges. The first one, we don't know about the unknown classes. We would not give any details about this one now. The second one is our focus. We not only have unknown classes we made, we also don't know about the occurrence frequency of each classes. The existing works overlooks the category occurrence frequency. They simply following the first GCD paper where the unknown classes occurs twice as often as the known class. However, in the real world, based on the long tail property of the visual classes, we are more likely to encounter known classes which we have labels than the unknown classes in natural environment. So in our work, we consider a more realistic setting where the unlabeled set is imbalanced with known classes more frequent than unknown classes. As shown in figure, for the known classes, for example, cat, dog, and rabbit, which are more easy to achieve labels, should also dominate the head distribution of the unlabeled set, while unknown classes, for example, lion, rhino, and panda, the animals we are not frequent to see that are harder to obtain, should belong to the tail part of the unlabeled set. For the IMBA GCD, there are two main challenges of this problem. The first one is how to estimate class prior distribution. And the second one is mitigating bias towards head classes. Tail or unknown samples are often misclassified as head or known classes, as models tend to focus on learning patterns from primary classes, which leads to poorer performance on minority classes. Next, I will introduce the method for the first challenge, estimating class prior distribution. Unlike conventional long-tail learning, LTL, we don't have any labeled information to handle class imbalance issue. So we update the class prior estimation iteratively by using model Excel prediction. For the second one, we apply constraints to pseudo-labels to align their distribution with the class prior distribution by using optimal transport algorithm, which can avoid the model bias, making less unlabeled samples misclassified as known class. And the whole process can be seen as EM framework. In E step, we estimate pseudo-label matrix A. In M step, we update the model parameters based on the overall loss function. So here we show the accuracy on the ImageNet 100. The row represent the imbalance factor. For 0.5, it represent original GCD setting. For 1, it represents the balanced setting. For 5 and 10, they represent imbalanced cases. So our method have achieved 14 to 18% improvement for the unknown class accuracy. So it shows the effectiveness of our method. And thank you for your attention. And if you have any further questions, please email to the following 2 email addresses. Thank you very much.
Okay, so we have all the spotlight speakers. Now it's the Q&A time. Does anyone have any questions? Please go to the mic. So maybe I'll ask the first question. So I'm really surprised by the performance of Viper GPT. And I'm curious, so you are using the code LLM. And how can we ensure that it's always output executable Python program?
Yeah, thanks for the question. This is something that we initially thought would be a really big problem to deal with, but it turns out that because we're using actual Python, so there are other works that you may have seen that are also trying to, like, very good work in this similar line of trying to use the reasoning abilities of language models, but most of them use kind of constructed languages or synthetic setups. Because we're just using Python, which is the language that Codex has been trained on the most, it turns out that, like, they turn out to be just executable by design, like by whatever they've learned beforehand. So ended up not really being a problem we have to deal with. Very non-answer, but thanks.
Okay, so you think the code LLM is powerful enough to generate ready to run Python programs?
Yes.
Oh, that's good.
Yeah.
Okay, we have some audience to ask more questions. Go ahead.
This is also a question about hyperGPU. So it seems in principle very similar to SECAN, where you're using steps. You spoke about one API. Did you experiment with trying to access multiple APIs?
So what we kind of did is, especially with the context length being 8,000 tokens for the model we were using, was we found that the primitives we needed for most visual things fit within a single context window. And so the differences we had were for different tasks, like for referring expressions or visual grounding, we just gave it less functions and collectively built up as we made, like, for more complex tasks, but we didn't try actually referring to different APIs, which would be very interesting. Like, we had one thing where there was access to language models as well, instead of just vision models, and that was kind of just defined as a separate function in outside of the class, but it was still given in the same context window. It'd be really interesting to do something like retrieve the relevant API and then use that as you need it, kind of thing. I think that'd be really cool. So yeah, for sure. Thank you. Hey.
So yeah, this is also about hyperGPU. So obviously there's generating executable code, but then there's also decomposing your reasoning steps into the right ones to actually answer whatever the query is.
Right.
Did you notice any interesting challenges with that, or sort of inconsistencies, or any kind of failure cases that you guys found challenging?
Yeah. So one thing was definitely the scope of different functions when it's not easy to delineate clearly, like in a docstring or something, that was a little difficult. So for example, I was saying with visual grounding, that is asking for, the second guy from the left, for example. And what you'd want is the program that finds people and then sorts them, etc., right? But if you just give it a function called find, there's no reason a priori that it shouldn't just have a one-line program that is return find guy on the left, right? Which it kept doing that. So that was one, like, scoping issue, was trying to tell it, like, oh, like, only use this for very simple atomic things. That was one of the issues we found by just, like, writing more about what the thing was and giving some, like, in the docstring, this was kind of inspired by actual documentation, though usually you wouldn't have such fuzzy functions. It was like, use this for things like blah, blah, and blah. Do not use this for blah, blah, and blah. So there's a little bit of prompt hacking needed for that specific set.
I see. Okay, so yeah, prompting can help resolve something.
Yeah. Though it would be better to have a way to, like, one thing we thought about but haven't explored yet is if you can get it to just figure out when a function is appropriate or not, and be able to decide what level of granularity to apply things at. Like, maybe you have a find function that can do second guy from the left, or something, in which case it should be able to figure that out. But we haven't done that yet, so that would be interesting.
And I suppose that would probably also have its own challenge.
Yeah, of course. Yeah.
Thank you.
Cool. Thanks.
Thanks again for the great talks and for questions. And next, So this year, our workshop are hosting two new challenges, segmentation in the wild and RoboFlow 100 for object detection in the wild. Let's welcome the challenge organizers and challenge participants to present. Thanks.
Hey, everybody. I'm Jake Solowitz. I work at RoboFlow as the founding engineer there. So today we're releasing a new benchmark. This workshop, it's RoboFlow 100, which is 100 object detection data sets. So I'll dive in a little bit on how we made this data set. So RoboFlow is a end-to-end CV platform, very akin to Landing AI, and we have a very generous free tier where we have public users building custom object detection models on our web application. So they can upload images, train, label them, and then train models. And we've collected some roughly 300,000 data sets on RoboFlow Universe. And these are all public that you can browse. You can see what people are actually doing out there, out on the ground, and what they're trying to do with fine-tuning small object detection models. And so from that larger corpus of 300,000 public data sets, we narrowed that down to 100 object detection data sets for this challenge. The way we did this is we first started by sorting our data set corpus by labeling hours, just to see which projects people were spending the most time constructing their supervision task. And then we filtered those for the idea that the task would be feasible, like maybe they had trained a model that was within a reasonable mean average precision. And then we were also looking for semantic diversity. So we're looking to capture projects across a wide, vast array of imagery. So the categories we ended up bucketing the data set into was aerial, video games, microscopic, underwater documents, electromagnetic, and real world. Real world being like kind of anything you might see in your normal visual sphere. And the idea behind this is to create sort of like a rich semantic space of imagery. So models that are being tested in different domains. And so the total data set comprises about 11,000 labeling hours. So this is a cool way we're able to draw some of the value of this data set out of the community that's normally naturally using our web platform. So resources for this, I put the GitHub link there, and then there's an exploration tool where you can get on and look at it just like you're normally looking at a data set. And the other thing I didn't include there is we have a REST API of the whole universe. So if that's of interest to you, we could potentially be working on collaborating on using that. Yeah, so some of my favorite data sets out of this. People are working on all kinds of things. So there's things like people are modeling how to do American Sign Language with their hands. They're doing infrared in their trail cameras to like count deer that are walking past trail cameras. Video games where people are labeling characters, sediments in microscopes. There's this really cool one of a fish market in Vietnam where people are classifying the different fish there. And then some aerial ones like aerial cow counting, stuff like that. And then here there's a little picture of what the data set clusters look like if you look at their clip vectors in a t-SNE plot, which is kind of cool to see that these data sets really are very like widely different than each other, at least in the way that clip sees them. And then yeah, some sort of initial results. So the purpose of the benchmark that we're working on, well, predominantly we kind of live in the yolk.
Sorry to interrupt, but there are like no slides visible.
Oh, really? Oh, here,
yeah, we are virtually connected.
Okay, here, we'll work on sharing this. Can you see those now?
Yes, we are able to see that.
Okay, great. Yeah, so the purpose that we were making the benchmark, well, so RoboFlow lives a lot in like the YOLO world where there's a YOLO lineage of models. And people are predominantly benchmarking on COCO for these things and wanted a little bit more real world generalizability of what people are actually doing, where they're actually taking these models and applying them in all these different real world domains. So that was kind of One angle was to work on people who are still working on these optimized fine-tuning routines. So that's models like YOLO V8, YOLO NAS, RDeter have all come out and now benchmarked on the RoboFlow 100 benchmark. And then the other area was for kind of like more what this workshop is focused on with general models, foundation models, looking at benchmarking those on how well they're able to generalize into these new domains. And then obviously to kind of track the relative progress of both of those. So some initial results that we kind of got out of the paper that was interesting. So as far as the fine-tuned detectors go, the COCO results actually flipped on that. And that's interesting because like if you dig into some of like the YOLO V5 modeling, there's a lot of like custom anchor boxes and things like that that are going on. That's a little bit better to be generalizing across data sets. And then the other thing is there's a pretty large gap in what you might perceive the gap to be in a COCO benchmark, where that's predominantly like web imagery, which might be something similar to the data set that the general models are being trained on. But when you actually go and take that off into more obscure imagery like aerial, microscopic, underwater, stuff like that, there's actually a bigger gap between those models there. Yeah, and then the fun thing that I have in the bottom right is we started to see people kind of naturally benchmarking on this data set with some new benchmarks coming out of like grounding dyno and YOLO NAS, stuff like that. So yeah, that's RoboFlow 100.
Thank you so much for Jacob hosting the OD 100 like RoboFlow dataset. Thank you so much. And yeah, hi everyone. Yeah, we are also organizing the segmentation in the vault challenge this year that is specifically focusing on the pixel level task and in the vault setting. Understand an image evolves from image level to region level and then to pixel level, and recent advances in part segmentation like motivated by Sam. And also here we're focusing on the pixel level task that gives more precise understanding, and also we focus on the interval settings that would be the real use case in daily life. And we are organizing this challenge. We have hosted image classification and object detection challenges last year that covers a wide range of real-world recognition scenarios, such as like recognize food, flowers, and also do some chest recognition tasks. And this year, we gather and organize segmentation in a vault challenge. For the segmentation in the vault challenge, it actually contains 25 data sets, span 85 classes, and also we have like 10,000 more training data, and also 2,000 more validation images.
Excuse me. Yeah, excuse me. The slides aren't shared virtually.
Sorry, can you see the slides now?
Yeah, thank you.
Thank you so much. Yeah, and here we visualize the data set in 2D coordinates. Each blob represents a data set, and the blob size measures like how many images are in the data set. And the blob distance actually measures like the semantic distance between each data set. And on the left-hand side, it is the training visualization, and on the right-hand side is the evaluation visualization. And luckily this year we get many entries to submit to our segmentation in about challenge. And here we show the zero-shot settings. And currently the rank 1 method is rounded SAM, which have 46 MAP and also follows Uninex, SAM, and ODICE and XCoder. We are the baseline methods. And today we are lucky to invite Uninex and ODICE author here, and they will give presentations later. And those methods actually, although they rank in different ways, but they have different rankings, but actually they are training on different data sets. They are training on different methods, and also their training strategies is different. So like it means that each methods have its own like priority, or they have its own like meanings of the own like benefit of their methods. We can see that here we compare the model example, like for example, grounded SEM are like example grounding dino and SEM, and also like other methods also takes use of the current very popular models and architecture, and they develop their own methods upon them. And also we show the training data on the right-hand side. And here we show some basic visualizations of our Xcode method. By observing those images, we can see that those are actually not like the well-defined images that we usually previously see. For example, in the ImageNet classification data set, that like the object is very like centric, something like that. There are some images that will with very dark background, and also like the image are taken with different angles that is more closer to real-world applications. And we benchmark this data set using our Xdecoder methods, and we benchmark of different tuning methods. But for example, here we tune the decoder and fix the backbone encoder, and the total parameters tuning are 39.3 million parameters. And we actually evaluate on different shots from 0 shot to 10 shot and to full shot. And also we compare each data set and different architectures. Can I ask, for the Zoom users, can you see the screen? I think never mind. So let's just continue present. Yeah, and also we try to tune less parameters. Like instead of tuning the whole decoder, we can actually tune the class embeddings and mask embeddings, which only contains like 1.5 million parameters. And in this setting, we also span through the whole data set and also provide many architecture as baseline numbers. And then we can tune even less. We only tune the class embeddings, which contains 0.26 million parameters. That is very computation efficiency. And I think some of you listened to Andrew's talk this morning. They actually tuned the model in a very few minutes. I think they only tuned part of their architecture parameters. And here we then visualize those results in a line chart. And there are two takeaways. The first takeaway is that image and text are largely improved in the segmentation results when only tuning with a small amount of parameters. So what does it mean? If we see compare A, B, C and chart, the interval, if we can zoom it. Yeah, that's great. So basically the lower baseline is it doesn't contain any image text paradata during training. And if we compare image text paradata, the model performance boost. And also the second takeaway is tuning more parameters helps when the sample number greatly increase, which means that when we tune more than 10 images, if we see the charts here, the gap enlarged. So for each kind of tuning, if we enlarge the graph, we can see that the parameter tunes are increased, and only after 10 shots there is a gap. So one takeaway is that if we want to do few shot segmentation or few shot tasks, actually we don't need to tune so much parameters. That is one of the takeaway. And actually, our baseline methods Xdecoder is developed under our motivation that towards a generalist approach for multimodal visual understanding. And along the way, we have two works. The first one is Xdecoder, and the second one is SEAM. And for Xdecoder and SEAM, actually, the high-level goal is we want to unify the previous methods that spans from image, region to pixel on the understanding level, and also on the modality level. We want to extend from vision language to audio, but we haven't finished audio yet. And those 6 well-known methods are like individual methods that can solve each point in a 2D coordinate. And our like high-level goal is to accomplish them in a single model. An executor spans the shaded area that covers some previous like tasks that, for example, Clips are doing, OpenStack are doing, and also Glib are doing. And here is the main like task that our executor can do. It actually uses the same model and same set of ways to do all the tasks, except those like yellow tasks. So basically we can do like referring segmentation, image captioning, image text retrieval, as well as all kinds of open vocabulary segmentation in a single model with the same set of ways. And with some composition capability, we are able to do referring captioning that does not need any like more models or like attached models. And attached with diffusion models, we are able to do referring image editing that is very interesting. And we will host a demo session tomorrow. You can come and see, yeah. And also, in light of executor, we also like explore like more modalities. Like instead of like we enter text or like do image level understanding tasks, we are also include like human interaction in the loop. And in the scene, we are able to do spatial references that a human can point the location in the image and to do segmentation tasks. And here is the task that we span that we can do like without any visual prompting. We can do all kinds of open vocabulary segmentation tasks, and with some like human input, for example, point, bounding box, and even like scrimbles, we are able to like also segment instance out. And with text prompt, we can do referring segmentation. And with some referring prompt, that is very interesting. We can refer a region of an image using another image and a region. Like we draw on the image with some like scrambles, and on another image, we will show like what is similar. For example, we draw a cat here and we see different cats here. And also our model is able to do zero-shot composition capabilities that we are able to integrate text and visual representations for joint references without any tuning or without any architecture change. So these are our methods. And also, yeah, that's end of my presentation. And we will welcome like other presenters, the author of ODEX to come to present his work. He's from UCSD and Jerry Xu.
I present our CVPR.
Okay, hi everyone. Yeah, before we started, just make sure Zoom audience can see the screen.
Yes, we can.
Okay, sounds good. Okay, thanks Xueyan for the introduction. And I'm Jerry. I'm presenting our CVPR highlight work, Odyssey, open vocabulary phonetic segmentation with text-to-image diffusion models. And yeah, we will have a poster session tomorrow, and please visit us. And in Odyssey, we propose a very simple method that leverages the diffusion model, which generates an image from noise, and leverage this model to, instead of doing image generation task, we do the semantic segmentation, panoptic segmentation task, which includes instance segmentation and the panoptic segmentation and semantic segmentation. And this is the high-level summaries, and I will go details in the following slide. And here are some qualitative results.
And in the ODIC, we found that the diffusion model is quite robust to segment categories in the world. And for example, since they are having the conference in the Vancouver, we have the previous image in the Canadian flag, and also have this Coco image. You go for the videos, and this guy is making sushi and cooking. And before I introduce ODIC, let me introduce the text-to-image diffusion model first. In the text-to-image diffusion models, it's generating a lot of amazing images just from pure noise. So given a initial noise map, the text-to-image diffusion model will iterate denoising this image, giving some text guidance and denoising it into very amazing images. This diffusion model is showing great image quality, compositionability, and the spatial relationship understanding. So in this work, we instead of using it as a generative model, we propose to use it as a recognition model. We decide to leverage the diffusion unit representation for the open vocabulary segmentation, the panoptic segmentation specifically. This is termed the ODIC, so it's an open vocabulary diffusion based panoptic segmentation. Before I go to the details of the ODIC, let me introduce the open vocabulary panoptic segmentation. So this is the standard panoptic segmentation. There are basically 3 tracks in the image, and the standard Coco dataset have 133 categories and all have the category track. So the standard model will identify this vehicle as the track. However, in the open vocabulary setting, we want to classify the categories in a more fine-grained details. So we want to classify them into something like a pickup truck and a trailer truck. And this will enable other models, maybe downstream models, maybe the ODIC itself, to understand the fact that the pickup truck needs a trailer truck to move another truck. And the formal definition is to segment and categorize any object, even the ones that are not present in during training. So for example, if the trailer truck is not present in the training, and the model is still able to segment it out and categorize it, this means the open vocabulary panoptic segmentation. And there are many categories in the world. There are also many methods to handle this open vocabulary in the wild setting. So to motivate us use the diffusion model to do this open vocabulary setting, we try to perform the k-means clustering on the frozen diffusion features. And we found that its frozen diffusion features is very semantic differentiated and show very localized information. This means that the diffusion model is generating the image, and then in the feature space, the image feature is kind of entangled. That's why it can generate a very high quality image with spatial understanding. This is our motivation. And besides the diffusion model, there's another popular work that is leveraged in the open vocabulary setting, which is the clip. So we compare the diffusion features against the clip features. I guess due to the resolution constraint of the clip and the other architecture perspective constraint, the clip feature is not that spatial distinguishable as the diffusion features. So this gives the diffusion features advantage for the open world recognition task over the clip features. And here is the training pipeline of the ODIC. Given an input image, we will first input the image into the text-to-image diffusion model with some step of noise. And we will extract the internal features from the diffusion unit. Before we get to the final features, we will also feed the image into the implicit captioner. By implicit, we mean that this captioner is not really generating the caption that is human readable. It's composed of image encoder and the MLP. And the snow icon here on the upper top is on the top left. It's meaning the network is frozen. So the MLP is tunable, and the image encoder and diffusion unit is frozen. We encoded the image and with the encoder and the MLP to get the text embedding. It's the so-called implicit text embedding. And we will feed this text embedding into the diffusion unit with the cross attention. To have an iteration about this implicit captioner, think the caption task as a high-level summary. So the caption network will generate a high-level summary of what's happening in the image. And it's very close to the global representation of the image. So the image, if the image encoder is good enough to capture the global information, the whole holistic understanding of the image, It should have the similar effect in the embedding space as the text embedding. So it's we use a clip as an image encoder here, and the tunable MLP only have very few parameters. And after we get the features from both this implicit captioner guided diffusion unit, we will feed the feature into the mask generator. The mask generator is just a meta architecture here. It can be replaced with any framework that could generate a panoptic mask. So it have two outputs. One output is mask predictions. It's just a foreground, background binary mask prediction. And another output is the mask embeddings, which is associated with the semantic information of each binary mask. For the mask predictions, we will supervise them with the binary mask loss, and it's class agnostic. And up to this point, we have leveraged the diffusion unit to generate the mask proposals, but it's still class agnostic. To classify each mask into the category we desired, we need to leverage the text encoder. So here we try two settings. One setting is use the category labels. The category label setting means that for each mask in the ground truth annotation, we have its category information. It's, for example, for this cat, we know this mask is corresponding to cat, and television is corresponding to television. And we will feed these categories into the text encoder, encode them separately, and get the text embedding. After we get the text embedding, we can perform the dot product between the text embedding and the mask embedding. Then we can supervise it with the cross entropy loss, which is very similar to the fully supervised setting of the object detection training, but it's the classification matrix is defined by the text encoder. And another setting is following the pioneer work OpenSec. It's used the image caption as a supervision for the image. So in the image caption setting, it means that only the ground truth class agnostic mask is available, and the whole image caption is available. There's no correspondence between the annotated mask and the vocabulary. We will extract the nonce from the image caption and encode each category with the text encoder to get another set of text embedding. To supervise the classification learning, we will use the grounding loss proposed by the OpenStack. Okay, and the inference is a little bit very simple. We use input image into diffusion and the text encoder, into the diffusion unit and the implicit captioner to generate a mask and the mask embedding. Besides the output from the diffusion unit, we also try to use the mask pooling method to pull the features from the image decoder, and then we could get another set of mask embeddings. Then during the inference, we can perform the dot product with two sets of text embeddings and perform a geometric means between them to get a final panoptic segmentation prediction. And to summarize, we are the first to leverage the frozen representation of large-scale text-to-image diffusion model for downstream recognition tasks, and it's also showing very promising results. And there's also in concurrent many other interesting work that leverage the diffusion model for other recognition tasks from low level to high level vision tasks. And this diffusion unit also demonstrates great potential of the text to image generation model in the open vocabulary panel segmentation. And the code is publicly available. Please feel free to ask any questions or come to our tomorrow poster session. Thank you so much.
Let's welcome the author of Unilex, Jianan, who is from Hong Kong University. Thank you.
Okay, thank you. I'm Jianan Wu from the University of Hong Kong. It's my pleasure to introduce our work, Universal Stance Perception as Object Discovery and Retrieval.
and consists of the following parts. Instance first.
All right.
As we know, object-centric understanding
Okay, it's my pleasure. My presentation will consist of following parts: the motivation of the inspection, the method using next experiment, and the video demos. Object-centric understanding is one of the most essential and challenging problems in computer vision. So in this work, we may discuss 10 subtasks, which are distributed on the vertex of the left tube. For the first type, the task need to find objects of specific categories, such as detection, instant segmentation, and MOT, MOTS, and VIS. For the second type of task, we need to find objects that are left by specific language expressions. And for the third type, the task need to find the objects by target annotation, such as SOT and VLS. So all above tasks aim to perceive instances of certain properties. So here is a natural question: could we design a unified model to solve all mainstream instance perception tasks once and for all? So in this work, we present a universal instance perception model of the next generation termed UniNext. It's a prompt-guided object discovery and retrieval framework. So the first key point of UniNext is the prompt generation. For experience-guided, it is used to transform the diverse prompts into a uniform formats. For expression-guided tasks, we leverage a language encoder such as BERT to encode languages. And for the category-guided tasks, we concatenate all the category names as a sentence and also use the language encoder for the sentence. For the annotation-guided tasks, the input is the image and its corresponding box or mask. So the 4-channel input image is processed by a vision encoder such as VisNet or ConfNext. Next, we perform the image prompt feature vision. The encoded prompt embedding is fused with the multi-scale visual features in a bidirectional cross-attention manner. It can enhance the prompt embedding by the image context, but also makes the original visual features prompt aware. So with the discriminative vision features and the prompt embeddings, the next crucial step is to transform the input images to the instance for the perception tasks. We resolve to the deformable data because of its flexible query to instance fashion. The deformable data is transforms an object queries into object proposals, but not all proposals are needed are truly referred by the prompting. So we need to further retrieve the truly matched objects from these proposals. Specifically, as shown in the right part of this figure, we conduct a product between the proposed features and the prompt embeddings. And the similarity score is used to retrieve the objects. Okay, here are some experiments of our UniNext. Okay, so lastly, let's see some video demos of UniNext. For the first type of category-based tasks, we use the category names as prompt, which are shown in the left top corner. And different colors represent the different objects. And the second type is the language-based tasks, such as RVOS. And for the third type of task is the SOT and SOT and the VLS. Okay, thank you for listening.
Thanks so much for Tina's presentation.
So next we will have two invited speakers this morning. The next speaker is Jason Liu. He is a research scientist at Allen Institute for AI. He obtained his PhD at Georgia Tech, advised by Professor David Park. His research is in computer vision, focusing on the intersection between vision and language and embodiment. He has published at major computer vision, machine learning, and robotics conferences, and is a co-organizer of the first and second VQA workshops at CVPR. And due to visa issues, Jason will be joining us virtually. Yes, so we see Jason is in the Zoom already. Let's welcome.
Yes, can you see the slides? Can you hear me?
Hi, Jason.
Oh, okay. So can I start?
Yeah, we can hear you well.
Okay, thank you.
Could you make the slides larger, maybe?
Yeah. A larger, okay. Let me see. Making this larger. 1 second. Okay, I think this is better, right?
Great, thank you.
Okay. Hi, this is Jason. So due to visa issues, I cannot joining the workshop in person. And the previous talk is really interesting. And today I'm going to talk more about this kind of like how can we like approaching these multimodal LLMs. So there are major 3 different approaches, which is coordination, adaptation, or training from scratch. So the first 2 part will be a summarization of the existing work. So I'll also share our ongoing effort and experiments about the training multimodal LLMs from scratch on the third part. So needless to say that large language models demonstrate strong capacities. So on the left, this is an example of a ChatGPT blog post about the model can accomplish the queries of the users, which is to write a short note to introduce himself to the user. On the right, people extend to the multimodal version of it. The model can take an image as input and successfully answer what is the unusual part of this image, which is quite interesting. The cool things about this large language model is they are open vocabulary by nature and have a really strong reasoning abilities. Right, so this is one of the examples showed in the GPT-4 technical report. So the user requests the model to read and summarize the InstructGPT paper, and the model can do an amazing job, which in general requires an OCR, reading figures and diagrams from all pixel spaces, and finally summarizing all of the content into short phrases. So large language models such as GPT 3.5 and ChatGPT by nature is unimodal, while GPT-4 is multimodal, as we all know, and can understand image as shown earlier. So recently, how to extending this language-only LLMs with ability to understand other modalities is a very active research area. So depends on how we use these LLMs. So we can roughly make into 3 different categories. So like adapting by coordinations, adaptations, and also learning from scratch. So roughly speaking, the coordination approach is directly using LLMs as a planner or coordinator to coordinate different modules for multimodal tasks, while adaptations align the multimodal features from other foundation models such as CLIP with LLM by fine-tuning a small set of parameters. And finally is of train from scratch, which is basically joint training the LLM from large-scale multimodal data set and thus naturally grounded across different modalities.
So just a little bit recap here. To use the modules as a coordinator, originally is the idea from the neural model network, which is originally back to 2015. So basically, given an image and a question, the modular network learns to parse the questions into structure composed of reusable modules. So each module will corresponding to one skills, such as find, describe, or some of like that. And given the strong reasoning abilities of these large language models, the coordination approach basically using this LLM to prompting structures that can capture the new multimodal capacities, so without requiring fine-tuning. So these new abilities including like video search, such as Socratic model, writing robotic policy, such as coded policy, and image editing, such as visual programming, and also calculators, such as the toolformers. So after this ChatGPT was released, there is a series of methods that trying to build based on the ChatGPT and can iteratively invoke the visual foundation models and solving the tasks in the dialogue, right? So the most complete one, like as I know, is React, like interact with many industry level APIs and search engines to provide a very strong performance. So these are the major, like three major pros to use this language model as a coordination. So the first, it takes advantage of existing language models, right, and other foundation models. And second, there's no training needed. So we can register new skills through prompting. And also, like it's like basically you can easily produce a visual output by calling generative model APIs and also other existing like generation models. Well, the cons is also pretty obvious, right? So there always be a communication bottleneck that between the tasks and queries, like between different visual foundation models. And also the abilities is bounded by the number of prompts. And and also the large language model itself is not improving since there's no training involved. So this makes us to consider the second way, right? So which is adapting large language models into multimodal LLM. So, so this multimodal visual learning and Flamingo are really the pioneering work, like in the community that trying to approaching that, approaching this like multimodal LLM. So basically, the Frozen, which is the first one, the multimodal visual learning, they first show that adapting vision encoder with Frozen LLM enables the visual learning. Right, so they basically giving us the kind of the visual prompt way that we can freeze the language models while fine-tuning the visual encoder. While Flamingo demonstrates like adaptation at scale. So with very cool like proposed like perceiver sampler and gated excitation, and also the interleaved visual test data, which is also used a lot of other existing work. So adapter-based method has rapidly developing over the last few months, right? So they can supporting various tasks, such as like vision language, which is the mainly one, like Flamingo, Bleep, Instruct Bleep, and all of the others. And also the like the embodiment, like agents, such as Weimar and Palmy. So one thing we can see is that the quality of the LLM matters, right? So llama-based models like really dominate the open source research. So after the llama was released. So another patterns we can see from all of this work is that it mainly focuses on language output, right? Except the GIL, which is enable this interactive retrieval and generation, like which is the most recent one. So like in the GIL paper, they are using a GIL mapper, so which is essentially another kind of Q-former, but instead of like mapping the input space, they're trying to mapping the output space, right? So I think this is a really cool idea that, and they further kind of like trying to align the output feature with the stable diffusion testing, like the encoder's output, right? So kind of like they probably cannot really kind of getting the details of the image context, but I think kind of it can generalizing and was able to kind of plotting very reasonable image figures with a Frozen language model is really cool. And so if we are kind of like seeing this, the success of these adapter recipes from the existing work, right? So the first one, we can roughly characterize into this modeling and data set. So from the modeling perspective, so first thing we can see is that the clip feature is really the core to enable this strong generalization. So with fewer data. So kind of like with linear adapter layer, like such as like the lava used, or with deeper adapter like QFormer from Split V2. But if you are using the deep adapters, so in general, like it requires conscious loss to make sure that after this kind of like deeper adapter, the kind of the representation still lies like concise in a space. And also another thing is that the zero out the visual features at the beginning of the training in general leads to better optimization. So this is generally found by the llama adapter and Flamingo. In terms of the dataset part, so existing kind of method finding that the existing vision language task can be prompted into multimodal industrial like instructional tuning dataset. So such as based on the Billy instruct. And also one of the very interesting part based on the lava is that the GPT for prompt visual chatting data and using the test annotations can really enable better alignment with the human preference, right? So I think this is also the authors like told that this is a core way to success, like they having a better data by prompting GPT-4. So to summarize, the adapter-based method is kind of like the most successful like approach so far. And the pros is that they have a very strong like generalization abilities, even on no novel task, right? So, and also they require minimum training with small set of parameters with filtered data. Well, there are still some cons here. So first is that there's majority of these models, they are limited with the language output, right? So kind of like because the model is pre-trained, if they are outputting other output, the model will suffer with self-characteristic forgetting. So like they cannot output like class vision task effectively, such as segmentation, etc. Right? And the second is that the large language model itself is not improving in general because they are freezing most part of it. Like this might be like the second part. Okay, so I'm moving a little bit fast because I kind of trying to catch a little bit more time for the next speakers. So the third part is that like we want to mention about is the training multimodal language model from scratch, which is still a very open source, open like research domain, right? So this figure is Cosmo 1. So basically that's just really a like a multi-modal large language model, so that is capable of perceiving image input and performing multimodal in-context learning, right? So it shows very strong in-context reasoning abilities with limited model size. And however, the one limitation is that the model still like only produce a text output, similar as Flamingo and other adaptation method. So I feel like this is one of this kind of like a missing part or like an unfortunate part of this work that I feel like it can be further improved, right? So it naturally like giving us a question like, why do we care about the multimodal output for like large language model, right? So there are definitely many things. So one of the things I want to point out is that so in general, like this multimodal outputs or multimodal like information, that it can kind of increase the robustness of the model, right? So it creating this redundancy, such as the system functions, even loss of one component that can achieving the task. Right. Also, it's a really good way to supervision, right? So the sensory systems that can educate each other without an external teachers. And also, there are some studies that this multimodal thing really enable the future learner, right? So the multimodalities might be the key to making the model as a future learner, more effectively. But also there are a lot of difficulties, right? So one thing, as we see a lot of in this like workshop, is that vision tasks are highly unnatural, right? So comparing to the language data. So the annotations is a lot of them are manually defined, and it's really exist in this kind of like the webly supervised data, like the natural data set, like you extracting from the like internet, right? And also, there is still no good way to efficiently representing the different outputs in the unified format, right? We do see a lot of good kind of like approach this like in the workshop, but a lot of them are still kind of requiring specific like tasks for specific like segmentation or detection. But yeah, we really want a good way that can really unify all of them. So yeah, so well, like I think all of this left the prior work that trying to kind of like exploring this in some sort of like scales, right? So on the left is one of our work that we called Unify.io, and which we basically trying to converting that the tokens into discrete all of these different vision tasks and other tasks into discrete tokens and training them jointly as a unified network, right? And the right figure is called TOBIT. So it can kind of doing this bidirectional kind of image generation and caption generation, and it shows really amazing image qualities here, right? So like basically showing that a single decoder that can actually doing this both kind of image generation and caption task, both in the same simultaneously. So and given all of this information, I would like to introducing some of our ongoing work for Unify 2.0, which is still working in progress. So like I will mainly showing some of the difficulties we see and kind of what we want to doing here, right? So the first is that we want to expanding the input modalities to kind of much more, right? So basically earlier we are only having an image input, and now we are trying to encoding with the image history and also with audio and audio history. Right, and also now the models we are trying, instead of like only decoding on only like the image and text, and now it's trying to decoding both, right? So image, text, and audios, and we were having a pre-trained like VIT VQGAN or like a VQGAN to kind of like serving as the tokenizers to translating this image and audio into different tokens, and which we're trying to understand by the transformer decoder. So another thing. Important thing is about the pre-training task, right? So kind of like how can we define a pre-training task that can naturally using the existing data while still like making the model has ability to learn different tasks, right? So kind of like here we are designing like basically say a task that is widely using in the community. So basically you are trying to masking do a denoising task, or you can do a purely generation, like if the mask is setting to all 0. Well, this also enables us to using a lot of like earlier like papers objective. So for example, this one is called Kurko, like from I think it's from like the NeurMist like last year, that they are trying to that basically giving like a same viewpoint of 2 different rooms. And if we are masking one of the room, trying to kind of reconstructing like using this, right? This is essentially finding the match point between the input image and reference image and learning the matching between them. Right, and also like because a lot of the major data set of our training corpus will be the videos, right? So we will also including this like kind of like multi-modal like image, video, like audio reconstruction or generation task. Like in this case that we were extracting like a discrete sequence of frames as the corresponding image and audios and trying to reconstruct the audio target based on all of this like contextual information. And also like embodiment is one of very interesting that enable actions, right? So like we also including some of this kind of like embodiment tasks that basically trying to like predicting the frame or predict like predicting what is the current positions or what is the next actions. So it's kind of enable like the actions for this model as well. Okay, so comparing to this kind of like Unify 1.0, so we are trying to really enlarge this data set of training. It's also leading to a very huge data set, and also now we are working on this kind of like multi-model instruction following data. So basically trying to really using the annotations of the existing data set and making them as a multi-modal instruction tuning. So instead of like only has test output, right? So each task and dataset has a detailed human and automatic prompt that describes the skills and the models to perform. And also hope this can be the first exploration of this, enable this multi-modal emergence of probability like properties. Okay. So to summary, like we for the training the multimodal LLM from scratch. So the first is that the pros is that the model can potentially interact with more modalities and learn from like more from the environment. Right? So like also this probably can give us one model for all that can both understand and generation, like for all of the different modalities, right? And the cons is that we firstly find that it's very hard to optimize. So this might leading us to worse LLMs. And for example, we're finding that like in general, the perceiver, like kind of like which trying to aggregating the image history feature is kind of like leading a lot of this gradient explosion problem. And the way to fixing them is actually having a really strong normalizations on the attention part, and also changing some of this attention logic to flow through to make it more stable. And also it requires more compute and compared to the adaptation-based method, like this is definitely one of this the bad part. And also you cannot easily utilize a pre-trained language model. Like what we see is that the success of all of the earlier approach is that they can using this llama or like these really strong models that really giving them a lot of benefit. Okay, so to summary, like we compare like the pros and cons for 3 different ways, like towards multimodal LLMs, right? So there's not really a best approach. It really depends on the applications and the needs, right? So I also having like kind of like open-ended questions, because I feel like this is our like important, really trying to kind of combining this LLM with vision and other modalities. The first one is like, what is the best way to represent different modalities, such as like it can easily understand the large language model, right? So we do see a lot of good ways, like XDecoder, like they're trying to querying like with arbitrary format, but what if this is in the context of that we want this to be a supervision of the language model output, right? So kind of do we need any adaptations on that? So, and the second one is that, can we increase the large language models multimodal abilities without direct accessing to the data modalities, right? So in general, and the concern of this one is because storing and accessing the data, especially for this dense label data like image, is very expensive, right? So if we can having a way that still enable the models to learn this multimodal like sense or still learns the kind of the world sense, that can maybe that's a good way that we can kind of improving based upon the current models like pre-trained language models. Yeah, that's basically all my presentations, and thanks for listening.
Okay, thanks a lot for Jason's talk. Since we are running behind, we'll skip the Q&A session and move on to our next and our last speaker in the morning, Katrina. Katrina is an assistant professor in Carnegie Mellon University's ML department. She has lots of great works on various topics and lots of work. So Zoom audience, this is a slide. Hi, Zoom audience.
Yeah, the slides work.
Good, good.
Yeah, thank you very much for your invitation and giving the opportunity to discuss our work. Okay. So I want to discuss 3 topics today. One is about open world detection in 2D images and 3D point clouds. The second is about the zero-shot open vocabulary video tracker out of pre-trained static image foundational models. And the last work is test time adaptation of pre-trained image classifiers with diffusion models. So up to 2 years ago, Ayush, Nikos, Ishita, and I were working on something that now is de facto and everybody uses. We wanted to merge language grounding and object detection
So here is the task of language grounding. You have a scene, which could be a 2D image or a 3D point cloud, and you have a referential utterance that mentions different entities. And the goal is to localize each one of those entities in the point cloud or the image. And back then, the standard thing would be you run first an object detector, get a bunch of proposals, and then you select the one that is relevant for your entity. So these models were bottleneck by they were upper bounded by how good the object detector was. And guess what? You run the object detector and it doesn't actually find the relevant entity. So what we proposed is what we call a bottom-up, top-down detection transformer, or BUT-DETER, like beauty-DETER, we call it, that operates in 2D images and 3D point clouds in the following way. You get the visual scene as input, which is being featurized with the visual encoder. You run also a pre-trained object detector, a general objectness detector, to find 3D bounding boxes in point clouds or 2D boxes in images. Then you take your referential description, you also featurize it with a text encoder, and you have cross attentions, and there's a decoder that finds each one of those referenced objects in the scene and links it to the corresponding entity in the referential, in the utterance, the input utterance. So what are the main features of BUT-DETER? First of all, we use a pre-trained detector. So if the detector can find the boxes, you can just directly attend to them. The model can attend to them if it wants. But we're not upper bounded by the performance of this detector. The input utterance can be either a referential utterance or a list of noun phrases, which is now a standard thing to do. So glibv2 took this idea and scaled it up tremendously and actually works really well, because now the task of referential grounding and object detection share training data, and we're able to get state-of-the-art performance on 3D language grounding. So here we see the SR3D and NR3D. Our model is much higher than the baselines, as well as a version of MDETER that we, it was a 2D model that we adapted in 3D. You can find the code of this model online, and very similar architecture works also in 2D images. Again, we had state-of-the-art or close to state-of-the-art performance to whatever was available at that time. All the different attributes of BUT-DETER contribute to performance. It is useful to attend to the object detector. It is useful to share training data between language grounding and object detection. And if you remove each one of them, then you do worse. Okay, so check some of the details of this project on our website, and you can use our code in 2D or in 3D. Next, so this basically was training foundational models. So that was the pipeline. In fact, we felt very lucky that one of the authors was able to be in Facebook at the time, and we were able to use the Facebook cluster to train the model. And guess what? We were able to train only once. So there was no time for hyperparameter search. And out of this one run, we got state-of-the-art results on 2D images, and we're able to add them in the paper. For the 3D point cloud, because 3D data are so much less, we're able to run it on our own GPUs. And we're working now on models that can actually merge 3D and 2D and use, annotations both in 2D images and 3D point clouds to boost the performance even further. The next work I want to discuss is zero-shot open vocabulary tracking. So here is a small video from UVA dataset, which is one of the pioneering datasets that says, let's just try to track anything that shows up in the video, okay? So we are inspired. So what happened before the explosion of open world object detectors, right? So tracking was doing very well, but it was doing very well for vehicles and people. And here is one work that we're actually very inspired from. This is a state-of-the-art object tracker. It's called Tractor. The title is Tracking Without Bells and Whistles. And what is special about this paper is that it doesn't train on video data. It takes a state-of-the-art object detector and repurposes it to become an object tracker. And how it does that? Well, it takes the bounding box at times the t-1 and propagates it forward with a motion model, then feeds that bounding box to a bounding box regressor of a person detector, and that bounding box regressor snaps back the motion propagated box to the person. And then once you have the propagated box, you feed this to an object to the person classifier that can tell you, yeah, this looks good, let's keep it, or you reject it. So in which case you terminate the track. You also run your object detector at every frame to spawn new objects as you need, and so on. So basically you have a state-of-the-art tracking without, to death fine-tuning and hyperparameter search, simply building upon, a masked CNN. And just to remind you how masked CNN would work back then, is you have your K anchor boxes, and indeed there is a bounding box regressor that takes that anchor box and adjusts. Okay, so this bounding box regression has learned personness, how personness is nearby, the vicinity of that box, and snaps it to the nearby person. Okay, so here is Tractor, a very highly cited paper, and the code is available and so on. And what we were kind of unhappy about is the following. The area of visual tracking has been over fragmented. I mean, because also the field is growing, so, and there are so many different benchmarks, and each one has its own assumptions. On the right of the screen is MOT, multi-object tracking datasets. These are familiar these are the earlier datasets that showed up. You need to track and detect people as they move around. There's a lot of occlusions and so on. So this is how the tracking field started. And recently we have this, track everything and segment the objects in the video, but guess what? I'll give you the ground truth mask in the first frame. So don't worry about it. So because the assumptions are so different, you cannot develop one method that you can use in both setups. And our basically motivation comes from the following fact. Can we take Tractor and rebuild it with modern components? Well, modern means Tractor was 2019, and now it's like 2023. It's not like a decade later, but can we use modern components and have a video tracker that we can use in all the setups? All right. And again, same as Tractor, we're not going to train on video data, and we're going to try to put together the neural modules of those pre-trained models in the right way to have something that works well across different settings. So here's our paper, which is under submission right now. Zero-shot open vocabulary tracking with large-scale pre-trained models. Okay, so what large-scale pre-trained models we use? We use the DETIC, which is an open vocabulary detector and segmenter. And we use SAM, which is segment anything, where you prompt using the bounding box and this recent software from Meta segments the corresponding object in the box. And we use pre-trained optical flow estimators to do the motion propagation. So modern Tractor, which we call OV Tractor from Open Vocabulary Tractor, because now we don't track only people, but we track anything, works like this. We have some bounding boxes at time step t, and then we compute optical flow between t and t+1, and we push forward those bounding boxes simply based on the motion. And then we use DETIC's bounding box regressor, okay, to snap the boxes correctly on the objects or parts or whatever we're tracking. We may be tracking heads alone or the whole body and so on, because now it's open vocabulary. And then we also use an objectness classifier to terminate the track. So if you see that essentially the box has moved somewhere where there's no high objectness, you need to terminate because we're going to start leaking, which is exactly what OV Tractor did using the person classifier in that case, as opposed to the general objectness classifier. And then you take that box and you feed it into segment anything to get the corresponding segmentation mask. And also at every time step t, you run a detector, all right, DETIC here, detector and segmenter, get new proposals. And if they don't overlap a lot with the track list you have, you need to spawn new objects, okay? And that's how it works, our OV Tractor. And here's some results on different object segmentation data. So now the question is, how well does this work? It works very well. So first of all, in UVO, which is a benchmark that indeed does not assume, is the only benchmark we found, it's about open vocabulary segmentation that does not assume ground truth mask in the first frame. We set a new state of the art with a big margin with respect to the previous approach. Yeah, and without having trained at all, of course, in that dataset, right? We use pre-trained and frozen modules from large-scale pre-trained models, as we said. Now, from YouTube VOC and Davis, already OV Tractor has competitive performance, again, without using ground truth mask in the first frame. So if we want to have a method that can work on both setups, we cannot assume that we have the masks given at frame 0. Okay, so this is the work that we are excited about, and of course we are building and trying to develop further and improving the re-identity component and so on. And the same method now can you use an MOT, which is the more standard computer vision single category type of tracking benchmarks, and again it works very well. Okay, so basically now we want to marry video segmentation and multi-object tracking. There's no reason to track them to track them with different methods because the same problems are in both. Okay, and my last part of the talk is test time adaptation with diffusion models. And our motivation was the following: how can generative models help discriminant vision tasks? This is a question that actually have been in our heads for like multiple years. Adam, who is sitting here, he organized in a couple of years back in ECCV a workshop exactly on that topic. And yesterday there was a workshop here that I tremendously enjoyed about generative models and how beyond generating beautiful images can help us on discriminative tasks, object detection, object labeling, part labeling, and so on. So just to give you, I mean, of course, this is something that worries everybody, not only us. There are some interesting recent works that try to address that point. One of them is test time training or test time adaptation with mask control encoders. Essentially, you have an image classifier, and somehow your classification accuracy goes up simply by taking a single test image and masking and trying to reconstruct the pixels back. So mask encoding is a self-supervised task. You don't need any labels, so you may as well apply it at each image at test time. And the interesting thing from that paper is that, yes, your accuracy improving, the more you can reconstruct the pixels of that single test image, the better you can guess the label. Okay, so we compare with them. And so here is our RSML 2023 work. Well, again, as I said, this question is on our heads for multiple times, where we essentially couple encoders and decoders to reconstruct back the pixels. And as you reconstruct the image better, then your encoding improves. Another very interesting line of work that is improving more and more is just use generative models for more training data, as opposed to trying to put them architecturally. And earlier also in this session, we had a very interesting work, Odyssey, right, that used the feature representation of a diffusion model for image segmentation. And here's another method that says, sorry, I think I discussed them the other way around. So this one is about generating synthetic data with diffusion models, and diffusion classifier says, you know what, you can take your text condition image generation and treat it like click. You can try to guess what is the text that maximizes the image likelihood. All right. So this is some related work. But again, I want to remind you, yesterday there was this beautiful workshop, generative models for computer vision, that asked exactly this question, very much what Adam also asked a couple of years ago. And there, Alan Buell, 8:45 in the morning, discussed analysis by synthesis. These ideas that have been around in the field, but haven't panned out because discriminative models become better and better and deeper, and they're just impossible to beat. Of course, in the course tasks of image labeling and object segmentation, maybe we need to go to more fine-grained perceptual tasks to really get the juice out of this analysis by synthesis, essentially inferring an image representation by generating back the content. Okay. So I'm very excited about this, despite the fact that it hasn't panned out yet. And now what I'll describe is one attempt. It's inspired by this idea, definitely not the right, end architecture on that, but let's see. I thought it was very interesting that gave good results. So here is an image of a rabbit. So what you can do with this image is you can add noise and try to guess back the noise with the text condition diffusion model. And if you put the rabbit embedding on the text conditioning, you will do a very good job on guessing the noise, much better if you put a wrong, instead of rabbit, you put chair, for example. Okay. So this is a standard text condition model, like, for example, stable diffusion. Okay, what you can find available online. So what are we going to do? We're going to take this image, feed it into, again, a pre-trained classifier, much like the diffusion model. These are both modules are pre-trained. The classifier will spit out a probability distribution of our different classes. And what we're going to do is we're going to take a weighted sum of all those language embeddings, and we're going to feed this into the text conditioning. And now we're going to backpropagate from the diffusion loss all the way to the image classifier. And guess what? Because essentially we're trying to maximize the likelihood of this specific image, the rabbit image, under a pre-trained diffusion model by trying to adapt the weighted probabilities of different language embeddings. And the right thing to be is that this image likelihood should become higher if I guess the right text, all right? Because that's how the model was trained. Yeah, so essentially what we do is we pair a discriminative model and a generative model, and the inferred state of the encoder is fed as conditioning to a diffusion model, and we try to maximize the image likelihood. Okay, and there is of course an incredible paper called mask to encoder diffusion models of mask to encoders that did show that you can actually use this type of pairing of discriminative encoder and diffusion model, and by generating images, essentially learn incredible encoding features, encoding representations. So this is what we do, and the results are as follows. So DiffTTA, which is diffusion-based test-time adaptation, improves image classifiers. So here we take ready pre-trained classifiers. We don't, train them ourselves and show, look, I do my DTA and I improve it. I just train it, a ready classifier, and I show I can do better by essentially doing this test-time adaptation for one image at a time at the test set. Okay, one image at a time. So basically, we're trying to guess what that image shows so that I can recreate the pixels under high likelihood with my text condition model. Now, where the boost is higher, the boost is higher if you consider, let's say, out of distribution images. Okay, so here you see different variations of the image in the data set. And here you can take a clip model, and we show that the clip can improve if you couple it with this diffusion model and you do this diffusion-based test-time adaptation. You see this where in the parentheses we show how much percentage it improves for every data set, and different architectures as well. Okay, so smaller or larger classifiers. And here is our model compared with the previous model of test-time adaptation with mask encoders that I just described in the beginning. And our DiffTTA does better. And across different backbones. So here's some nice visuals that this what happens during adaptation. As you see, I give you a single test image, and over time, the diffusion loss is minimized, which means the likelihood of the image is maximized, and also the cross-entropy loss, so the classification accuracy increases, okay, which is exactly what we want to happen. And here's another example. And of course, finding better ways to couple discriminative models and generative models is something that I'm very excited about, and I hope to see more in the field. So thank you very much for your attention. I want to mention that the first work was done by Nikos and Ayush. The second work, which is about video tracking, was done by Yuan and Adam. And the last DiffTTA was mainly driven by me here. So I thank very much the students for their work. I'm here to just describe their work, okay? So and thank you very much for your attention.
Do we have any questions? Please go ahead to the mic. So I'll ask the first question. So using diffusion models for understanding tasks are really amazing. And you are mentioning it's a text conditioned model. So have you tried to do it with open vocabulary classification, like using some very long, a bit longer sentences or free-form text for the classifier?
Yes, so this is a great question. So right now we have a fixed set of labels, okay, which can be very long, like thousands, and then you take a weighted sum of those. So because of that, I say the prompt should be, I mean, you can also have two, for example, you can have category at, and then you have again another list of what can happen at the kitchen, at the bathroom, or at the living room, and so on, and again try to search over it. So this is interesting what you're saying, but right now the way we have set it up is over a very long but fixed set of prompts.
Go ahead.
Thanks for the great talk. I have a quick question about, so I noticed that the ResNet boost is much higher than the transformer boost in the DiffTTA. I wonder if you think that architecture can be relevant to, a relevant factor.
Yeah. So the deeper and the larger the encoders are, the much harder is to improve them with test time adaptation. And in fact, many papers on test time adaptation, what they do is they take a very kind of crappy encoder and they show, look, I have a big boost, which is also useful, which shows that iterative perception actually allows you to have much shorter models. But yes, this is what happens here. The stronger the encoder, it has memorized everything, the harder to improve it at test time.
Your talk is raised some very interesting possibility from commercialization perspective, only particularly in healthcare applications, when you freeze the model and do inference only at deployment time. What you're saying is that the inference itself is trainable with the diffusion approach for your individual. I wonder what the implication would be for regulatory purposes that happens. I don't know, what is your impression of applying this to medical imaging data sets? And that has improved performance on, because there the discrimination problem or the label sets are very different from the benchmark data sets that you're training on.
Very good. So your question is essentially, out of domain, this helps most. A medical image domain is a place where we do have a lot of out of domain images. So there are chances that these models are going to do well there. Yes, I do believe so. I do believe that if we go to iterative perceptual architectures, we will be able to do much better out of domain. We should be able to generalize way better. Okay. So we are actively searching on improving exactly this model to do this in a much wilder setup other than just image classification, like more fine-grained tasks like object detection, segmentation, and so on. Yes, I think your setup that we are imagining is exactly right. Yeah.
Do we have any more questions from the audience? Or any Zoom audience? Feel free to ask questions. Okay, if not, then let's thank Katrina again for the great talk. I also learned a lot from actually all the talks today.
Thank you.
Yeah, and this is all for our morning session. Our afternoon session where we have sorry.
What about the runtime when you're going to test time training? So going through the diffusion model, how long would it take to do it? You know,
Well,
for every
yeah.
single